Hello, hello, testing. Hello, hello. सुनील जी वो हेलो सुनील जी। जी सर। हाँ उसको प्ले हाँ हाँ सर बिल्कुल। आपकी आवाज को नहीं नहीं नहीं। हेलो सर। गुड मॉर्निंग। गुड मॉर्निंग सर।
प्ले हो रहा है कि नहीं हो रहा है?
नहीं, आई थिंक इट इज नॉट प्लेइंग। सो
सर गूगल मीट ये जो है फ्री वाला है ना, इसलिए इसमें सारे ऑप्शन जो है वो कर
अच्छा।
दिया है। तो वीडियो चल सकता है या फिर उसका पीडीएफ उस पर चलाया जा सकता है, दिखाया जा सकता है कि थोड़ी देर देख लें लोग।
अच्छा,
आई थिंक इट्स ओके।
वीडियो ही चला दीजिए।
लेकिन सर ऑडियो आएगा नहीं
ओके,
सर।
you can play the video for some time. You can share. Please share. And also join.
लगन ने आगे मान लिया।
सर आप भेजे इसमें लिखा हुआ भी है।
लिखा हुआ है लेकिन वो वीडियो नहीं।
अच्छा वीडियो में
वो वीडियो प्ले कर दीजिए जैसे लिंक स्टार्ट करेंगे।
पहले उसको ऑडियो ये वाला ये
मैं ज्वाइन करता हूँ। मैं भी इसमें ज्वाइन करता हूँ।
वो वाला पुराना तो पुराना चलिए यही ठीक। कौन सा था? ये वाला चला ये वाला नहीं ये ये नहीं यही चला। और पीछे अब स्क्रीन शेयर कर देते हैं। म्यूट है ना।
Dr. Jai, if you're playing, you have to unmute yourself, I guess.
Hello.
Yes. Only video will come.
Hello.
There is no
Abaji.
sound.
Hello.
Yes, sir. Yes. Hello.
कोई इसका म्यूजिक नहीं आ रहा है.
Sir. So audio नहीं आएगा. Audio will not come. There is some technical issue.
Hello.
Audio. It will not come, sir.
Oh, I
It will
see.
not come. Only video will come. Audio will not
Okay,
come.
okay, okay.
But last time it came, na? Hello.
No, there is some
Yes,
issue
sir.
now.
Hello.
Yeah. मैं इनको भेज देता हूँ तब वो हो सकता चल जाए.
Now there is some changes
Sir.
in Google Meet, some policy. So there is some changes in setting. That's why it will not come now.
Okay.
So it's okay, I think.
Som sir. Hello.
Hello. Hello.
Good morning, sir.
Good morning.
কখন
Good
start
morning.
হবে কখন?
Start এক্ষুনি হয়ে যাবে. দাঁড়াও.
Hello.
এই 4:45. Let some people join. Only 9 people have joined. Yeah, it is going to start shortly.
তো মধুর মনে অডিওটা চালিয়ে স্যার audio, there is audio na.
Let me check in my mobile.
Sir, audio will not come because we have tried. It will not
Tell them
come.
to
Only video will come. That is not right. So we have tried. There is some, earlier there was some options in option meet. Now that option
Not a
is removed.
video.
So, yeah. So no audio will not come now.
Lavanya, can you play that one
Hello.
in your mobile and just put it here quickly?
I can hear it,
Audio
sir.
of the
Now it's already. I think that we could have done, but now it's already. I think 8:45.
Okay.
So I think
Yeah. There is some delay. Your voice is not coming.
no, I have muted. So
Okay.
I'll start now. Let's. I'm waiting for.
Another.
Yeah. So Ramki sir has joined.
Yeah.
I'm waiting for Professor Aladi to join. So, अभी सबको आप एडमिट करते गए हैं ना?
फ्री वाले में बंद कर दिया। गूगल मीट जो मीट फ्री है उसमें से पीपीटी बंद कर दिया।
Hi, hello sir.
Hello.
You are able to see me? Hey, where is my
Yes,
movement?
Okay. So
Oh, you
Mr.
are
Aladi has joined.
Yes, hi. So we just need to double check.
Yes.
I'm going to show you the two separate, one is the full slides of the talk and the other one that I'm going to show at the end.
Yes.
You have to tell me whether, first I'm going to show myself.
Okay. Yeah.
Okay. You got to tell me whether it should be in this form or any other form. So what do I do now? Do I share?
So you first on your video. Your video is not available, so you can.
How do
The video is available.
I go to present now? Do I go to present now?
So you go to present now.
Yeah. And then I go to
Entire screen.
entire screen.
Yes.
Problem. What the problem is? My camera goes like this. Okay, now I go to that center and I do share.
Yes, share.
All right, and now what do? I have to click on the
PDF which we want to share.
it says I'm presenting to everyone.
Yes, but it is not visible to us.
Sir, you just have to click Acrobat, the Adobe Reader files.
So are you able to see the Ramanujan bust?
Yes,
No,
yes.
okay, just let me see. I'm not able to see in this my screen.
Yes, it is visible.
It's visible for us as such. Yeah.
It's visible fully.
No, sir, you have to make
Yeah.
it. You can just press Control L for full screen. Then it will be on full screen.
Yeah, but in the beginning of the talk, I want to just my face to appear. Only later I want to do this.
Yeah, so
You can repeat this process again, sir. Yeah.
Okay, now this is full screen, is it?
yes,
It's not full screen, but still, yeah. I mean, it's okay.
I think it is visible.
So I think under view, I should go for full screen.
Yes, yes.
But
Yeah. Correct? Now you are able to see full screen?
Yes, sir. Yes.
Okay, now, so how do I minimize this so that I can see myself?
So you can just
you can-
press this escape button, ESC on your keyboard.
Sir, you can just go back to the tab that wherever you are presenting.
No, I have to do escape.
Yes, escape.
All right.
Yes.
Now, hold on. I don't want to make a mistake. Now I will show you the other one. Just tell me whether you are able to see it. Are you able to see this?
Yes.
Yes.
Catherine Brinkman.
Yes.
Okay, good. Now, at any point, you can give me instructions as I'm giving the lecture, okay, whether I should what I should do. I don't mind. Okay, so that is fine. Now to see myself, I should do stop share.
Yes.
Yes.
Okay. So Mrs. Lavanya is on the screen. So she's going to be helping me.
Yes, she'll be there. Yes.
I'll be there around. Yes, sir.
I see 3 names. Subir Das,
Yes.
then Tanmoy Som,
Yes.
Lavanya, and you, Abhash. I see 4 of you.
Yes. So
Good
there are
morning,
many
sir.
participants. It depends.
Good morning.
on,
Good morning.
Morning.
Good morning, sir.
Yes. It's good night to me. It's
Good
10:30
night.
p.m.
Yeah.
Yeah, good night. Good evening,
Yeah.
actually. Good late evening.
So,
All right.
okay.
So I see myself in very small form on the right-hand side top.
But we
Okay,
see you
no
in the
issue.
middle, sir. Don't worry.
That is fine. Okay, you are able to see me. That's all is important.
Yes.
Okay.
So, okay. So maybe you can start.
Yeah.
Well, it's not yet 9, is it? I mean, it's a little bit before 9, isn't it?
Yes.
Is that
Yes. So,
Ramki?
Hello, good morning. Good evening.
Hello, Ramki. How are you?
Yeah, fine, fine. Nice to see you.
Nice to see you. Yeah, it's 10:30 p.m. for me.
Yeah.
I'm actually in a huge log cabin
Okay.
in the middle of the mountains in Tennessee.
Oh, okay.
This is a vacation that has been booked by my daughter.
Okay.
So we are 14 people, all members of my daughter's family. There's Samandhi, everybody is here.
Okay.
So luckily, because it's 10:30 p.m., all the activities during the day is over. We went
Oh.
up, everything is finished.
Yeah.
And tomorrow morning, my time, 8 a.m., I'm doing the chairing the session for the Shasta Ramanujan commemoration lecture, this year's winner.
Yeah.
It will be 6:30 p.m. IST. You might receive the invitation.
Yeah, I saw that, yeah.
Because I asked Shastra to send the invitation to all people who have spoken at the Ramanujan conference in Shastra. So, and you have.
Okay.
So, I received the invitation from them.
Yeah. Thank you.
So, it's kind of back to back for me.
So maybe we should start our program formally then. So
You want to start now?
not
No,
now.
5
Maybe
minutes.
I'll
It's still 9:25, right?
yeah. So I just see the participants. I'll just give an overview of what is the conference, how we are going to conduct. So I'll just give an overview in this 5 minutes. So good morning, everyone. So I give a very warm welcome to all the speakers and participants of this international conference on number theory and algebra. This 2-day online international conference on number theory and algebra is conducted to celebrate the 133rd birth anniversary of mathematical genius, Indian mathematical genius Srinivas Ramanujan. And the aim of this conference is to bring together experts in various areas of number theory and algebra. In addition, this conference will aim to motivate and encourage the young researcher and give them exposure to the recent development in these areas, and in particular to the areas influenced by Ramanujan. So it is a pleasure to have you all at this conference, which is jointly organized by Department of Mathematical Sciences, IIT BHU, and the Teaching and Learning Cell at IIT BHU. So let's start our program. Now I request Professor T. Som, Head of the Department of Mathematical Sciences, to formally welcome the speakers, participants, and give an overview of the conference. So over to you, Professor Som.
So, very good morning, very good evening to all the delegates who are present here right now. We are celebrating 133rd birth anniversary of Srinivasa Ramanujan Iyengar, who lived here only for 32 years, and he has contributed a lot to the mathematical world. His famous Ramanujan Hardy Ramanujan number 2719, like that, Mach theta function, Ramanujan conjecture, Ramanujan primes, Ramanujan sums, etc., are famous. Then, though he had no formal education, but he has done no formal training in mathematics, pure mathematics. He made substantial contributions to mathematical analysis, number theory, infinite series, and continued fractions, including solutions to mathematical problems then considered unsolvable. Ramanujan initially developed his own mathematical research in isolation. Accordingly, Hans Isaac. He tried to interest the leading professional mathematicians in his work, but he failed for most of the part. But he had to show them was too novel. What he had to show them was too novel, too unfamiliar, and mostly presented in unusual manners. Seeking mathematicians who could better understand his works, in 1913 he began a postal communication with Professor Hardy at the University of Cambridge, England. Recognizing the works of Ramanujan and as extraordinary, Hardy arranged for his travel to Cambridge. In his notes, Hardy commented that Ramanujan had produced groundbreaking new theorems, including some results that defeated me completely. So these are the things which interest all of us. He was the first Indian to get Fellow of Royal Society of London. Okay, so in this 2 days program, we have 2 plenary talks by Professor Krishna Swami Aladi and Professor Bruce Bunt, 20 invited talks by experts from all over India and outside abroad, 15 contributed talks by postdoctoral students all over the world. I formally welcome you all on this occasion, auspicious occasion. This time we are not have any plan to publish any proceedings, but we have a plan to again do it every year, and maybe this next time we will bring out a proceedings of this conference or such conference. So once again, I formally welcome you all to this program. Now over to Abhash.
Okay, thank you, sir, for welcoming the speakers and participants and also giving an overview of the conference. So as you all know, this program will be conducted on Google Meet, and also it will be live streamed through our YouTube channel. And the link of YouTube is already shared on our web page of the conference as well as with the registered participants. So in this Google Meet, contributed speakers, and some of the participants are there, so they can ask their questions in chat box, and that will be conveyed to the speakers. Also, the participants who are watching on YouTube, they can ask their questions on the comment section of the YouTube, and that will be conveyed to the speakers by the moderator. So I would like to request everyone to please keep your microphone always mute, so that it will not cause any echo and disturbance. Now I request Professor V. Ramakrishnan to chair this first plenary talk. Over to you, sir.
Okay, welcome you all. I think I'm audible.
Yeah, perfectly.
Okay, so welcome you all. So I have the privilege of introducing the first plenary talk by Professor Krishna Swami Alladi. So he was born in Thiruvananthapuram and did his undergraduate studies at the University of Madras, graduating in 1975. While studying undergraduate, he wrote to Professor Urdish concerning his research on the function that maps each integer to the sum of its prime factors with repetition. So Urdish, when he came to Madras to meet him, their collaboration started, and then that was his first research paper. He collaborated to work with Urdish. The two mathematicians co-authored 5 papers in total. After that, Professor Alladi went to the University of California, Los Angeles, for his PhD. He completed PhD in 1978 under the supervision of Professor Strauss. He was awarded an alumni medal for the best thesis. After his PhD, he had held several postdoctoral positions, visiting positions at prestigious institutes like the University of Michigan, Institute for Advanced Study Princeton, University of Texas, and University of Hawaii. He was an associate professor at the Institute of Mathematical Sciences, Chennai, for 5 years before moving to the US. the University of Florida, where he is a professor now. He started his career in classical analytic number theory, but later he was infested with the Q disease caused by an overwhelming love for Q series and partition. I think these are the words of Professor Askey. He has made significant contributions in this area, some in collaboration with the leading experts like Andrews and Basil Gordon. He is the founder and editor-in-chief of the Ramanujan Journal, and he is also the chair of the Shasta Ramanujan Prize Committee, which recognizes and awards annually outstanding mathematical research by very young mathematicians of age less than 32. So today's talk will be on Ramanujan's place in the world of mathematics. Over to Professor Alladi.
Thank you, Professor Ramakrishnan, for your very kind introduction. May I just add, it is a pleasure for Professor Ramakrishnan Ramki for me to be introduced by him, because he mentioned me graduating from the University of Madras. We could have added Vivekananda College, because that is a common bond between me and...
Sorry, I missed it,
Both of us are hailing from Vivekananda College. I want to thank both Professor Jha and my former PhD student, Dr. Ankush Goswami, for inviting me to this talk. Normally, December 22nd, I am in Shasta University, Kumbakonam. This year, the conference is not being held, although the prize winner has been announced. In fact, he's going to be giving his talk at 6:30 p.m. Indian Standard Time on December 22nd, today for you and tomorrow for me. So because at Shastra, the must come there and receive the prize, and not only that, they show all the things relating to Ramanujan, like the home and so on. So that's going to happen next year, along with the 2021 winner. So that's why I'm not at Shastra this year, and also because of coronavirus, we are not traveling. So it turns out I was free today, December 22nd for you, and it's a pleasure for me to accept the invitation. Thank you also to the head of the department, Professor Som, for his kind words of welcome. I had heard a lot about Banaras Hindu University from my father, because my grandfather and Sarvepalli Radhakrishnan, who was one of the vice chancellors of Banaras Hindu University, were very close friends and contemporaries. So through them, I have heard a lot about BHU. And I had the pleasure of actually visiting Banaras Hindu University maybe 3 years ago or 2 years ago, when there was a conference of, I think it was American Math Society, jointly arranged with the one of the Indian math societies in BHU campus. And I was really thrilled to see the beautiful campus with the old historic buildings and so on. So it was a very nice visit. I was invited by Professor Adhikari, who had conducted a session there. So anyways, I'm very glad to be able to present this talk to you today. Now, this talk, Ramanujan's Place in the World of Mathematics, is actually based, so to speak, on my book, Ramanujan's Place in the World of Mathematics, which is published by Springer. So I will talk about that at the very end. But the first time I gave this talk was actually in Mauritius, where there is a Ramanujan Trust. And that was for a very general audience. I'm using the same slides, but to this audience, I'm going to infuse more mathematics in it and not necessarily provide you the background of Ramanujan's life and so on, which is familiar to all of you. Okay, so I'll go straight into the mathematics and skip the things relating to his life, because I think it's familiar to all of you. And if you have any questions about that, you may answer at the end. I also gave this talk at the IIT Gandhinagar, again to a group of very talented young students, and therefore this talk was quite well received. So I felt it would be appropriate to give the same talk here to this group, but as I said, with more mathematical emphasis. So the idea here is that we understand Ramanujan's mathematics better, and therefore are able to get a proper assessment of his place in the mathematical firmament by comparing both his life and his work with those of other mathematical luminaries who have things in common with Ramanujan, like Euler and Jacobi and Hardy and Littlewood and others. So I'll do these comparisons as I go along. So let me start the lecture proper. and you tell me whether you are able to do full screen now, okay? So you may have to just guide me a little bit because I'm not so techno savvy. Are you able to now see the full screen? Oh,
Not now.
Sir, you have to go back for present now again.
oh, I have to start all over again.
Yes, yes.
Okay, I'll do that. Hold on there for 1 second. I'll do it. It's going to be easy. Then I go to entire screen. Then I have to select that. Then I have to do share.
Yes.
And then I have to hit on this thing, right?
Yes.
Oh, hold on. There's some interference. Hold on. I'll now hit on this. Okay. Now you're able to see.
Yes.
Yes.
Okay. I'll now make it full screen. Okay, good. So I'm just starting with this fantastic bronze sculpture of Ramanujan, the bust of Ramanujan made by the American sculptor Paul Gramlund. I'm going to just back up one slide just to say that this was a talk that I gave in Mauritius in 2017. But as I said, I'm going to present a lot more mathematics in this talk. Just a couple of things to set the mood. G.H. Hardy, his mentor, said that he was the most romantic figure in mathematics and in transformations of infinite series and products. Only Euler and Jacobi could be compared to him. Now, this is an interesting statement made by Hardy, and this was actually conveyed to me by Paul Urdish, my mentor. So it was Urdish who told me about this. So Hardy had, of course, this habit of ranking mathematicians and also making statements about the relevance of various topics in mathematics and so on. So if you rank mathematicians purely on talent, he gave Ramanujan the perfect score of 100. The great German mathematician Hilbert got a score of 80. Hardy gave Littlewood the higher score of 30 and himself 25. That also showed the respect and regard he had for Littlewood. And also it gives you the gulf between Hardy and Ramanujan, 25 to 100. So it also shows the high regard he has for Ramanujan. Richard Askey had also said that the last notebook of Ramanujan is comparable to the work of a lifetime of a very great mathematician. Now, here are some of the areas which have been influenced by Ramanujan, which have continued to influence. Hypergeometric and Q hypergeometric series called Q series. Partitions and what McMahon used to call combinatory analysis, which means use of analysis to understand combinatorially various objects. Then additive number theory in a broad sense by the generalization of the Hardy-Ramanujan circle method. So this includes Waring's problem and many other things. Probabilistic number theory, which emerges out of a Hardy-Ramanujan paper on the number of prime factors. Elliptic and theta functions, and a whole variety of topics I have listed here. And I want to say that the Ramanujan journal, which was started in 1997 and now published by Springer, is actually devoted to all areas of mathematics influenced by Ramanujan and definitely includes this list that I have given here and more. So I want to skip all this because I think as people hailing from India, you know many things about Ramanujan's life and the fact that he was inspired, at least the people around him used to say that he was inspired by the goddess of Namakkal. I will have a comment later on the goddess of Namakkal when I talk about some mathematics. The goddess used to come in his dreams. The other thing also is that car synopsis that he read influenced his style of recording his results in his notebooks. So car synopsis, as you know, is a sort of like a guidebook for people taking the TRIPOS exams, and it lists a whole bunch of results one after the other without really giving proofs, but every now and then there are some hints given, and Ramanujan's entries in his notebooks are in a very similar style to Carr. Now, one of the things, it turns out that as a young boy, he rediscovered for himself Euler's formula for e to the I theta, and of course was disappointed to find it in Loney's trigonometry. Now, here is an interesting thing that can be said of Ramanujan as a schoolboy. He created his own birthday magic square. So there you see 2212, 1887. That is his birthday. And then here's a 4x4 magic square. I just want to make one comment here. It's very easy to find formulae to generate odd dimension magic squares. We know 3x3 is almost trivial. 5x5, 7x7. It's more difficult to construct magic squares with an even number of entries in a row. So those of you who have not visited Kumbakonam, I just show a few pictures. Here is Ramanujan's home as renovated by Shasta University. So you see all those plaques in the front. It says it's owned now by Shasta and opened by Abdul Kalam, the President of India. Here is that cot in that one single bedroom there in Ramanujan's house. And Ramanujan used to sit on that windowsill and see the passers-by on the street. So that's why I took this picture. And it's an old style house. It's got this well in the back. This is the one main room in the center. There you see the Gopuram of the Sarangapani temple as seen from Ramanujan's house. As soon as you come out of Ramanujan's house, a close-up view of the Gopuram of the Sarangapani temple. This is the town high school in Kumbakonam where he studied before joining college. This building at the bottom is the one which houses the library of the town high school. And that morning prayer hall is named after Ramanujan. It's called Ramanujam Hall, as he used to be known in his Iyengar community. And below is the Government College of Kumbakonam. Now, of course, Ramanujan knew that the local mathematicians were unable to understand his higher flights. So he communicated his findings in 2 letters to Hardy. I just want to focus on 2 formulae in the letters because I'm going to return to these formulas. So here is one very remarkable formula involving a continued fraction. And Ramanujan does the evaluation of this continued fraction in terms of the reciprocal of the golden mean, square root of 5 minus 1 over 2, and the golden mean itself, and some powers of this. It's an unbelievable evaluation. And another result that is emphasized by Ramanujan in his letters is that if you take the reciprocal of the power series 1 minus 2x plus 2x to the 4 minus 2x to the 9 and so on, the powers of x are the perfect squares. And of course, you have 2 everywhere except for the very first coefficient. Ramanujan says that the coefficient in the expansion of this power series is the nearest integer to this particular expression involving the hyperbolic cosine and the hyperbolic sine. I will have a comment later about this in connection of what Selberg said about this formula. Okay, next. Here is a page of from Ramanujan's letter to Hardy. That evaluation that I was talking about is what you see as entry 1.12. And this coefficient statement is 114. Okay. Now, not everything that he said there is correct. For instance, 115, which is a statement on the estimate for the number of integers up to x, which are the sum of 2 squares, given by means of this integral, and the theta is a little too sharp. He's thinking of the logarithmic integral approximation to pi of x. The main term in this is correct, which is x over square root log x, but then afterwards the expansion is somewhat different. So there are some slips in what he claimed in his letters to Hardy. All right, so anyway, Ramanujan went to England after getting his mother's permission, and there are 2 stories to this. One story is that the goddess of Namakal came in his mother's dreams and allowed her and told her that she should give permission for his son to go to England. So arriving in England, this is a picture of Trinity College for you. And Ramanujan, of course, had honors conferred in England, Fellowship of the Royal Society and Fellowship of Trinity. I wrote this in the opposite order. He was actually denied the Fellowship of Trinity first due to some prejudice. So Hardy successfully, but with a great deal of effort, got him the Fellowship of the Royal Society, which of course is a bigger honor. And once that happened, the people at Trinity College felt embarrassed and the Fellowship of Trinity followed. He fell in England due to his peculiar habits. He was a strict vegetarian, and he was also very particular to the type of food he ate, and it couldn't be given during wartime England. So he came to India in 1919 and died in 1920 at the age of 32. Okay, that's briefly his life. So let me begin with some mathematics. Now, Ramanujan liked to surprise people. He liked to shock his student classmates. He liked to shock his teachers. So one of the things Ramanujan showed his teachers was this statement: 1 plus 2 plus 3 up to infinity is minus 1/12. So on seeing this, his teachers said that he doesn't seem to understand divergent series, that he should go and start studying books on convergency and divergency of series. Now, let me give you Ramanujan's within quote proof of this statement. So he says, let's put 1 plus 2 plus 3 dot 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 equal to C. Just give it a symbolic representation. Now multiply C by 4, so you get 4C. And what you do is you write the 4 underneath the 2. You write the 8 underneath the 4. You write the 12 underneath the 6, and now you subtract. So C minus 4C is minus 3C. And then your series now becomes 1 minus 2 plus 3 minus 4 plus 5 minus 6 and so on. And that's equal to minus C. Now at this point, Ramanujan makes a statement, which is a correct statement, that 1 minus 2x plus 3x squared minus 4x cubed dot 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 is 1 over 1 plus x whole squared. Yes, that's a correct statement. But as we all know, it's valid only for absolute x less than 1. So what Ramanujan says here is, he boldly says, put x equal to 1 in that series, and what you get is 1 minus 2 plus 3 minus 4, etc., the series that we saw on the previous slide. But on the right-hand side at x equal to 1, 1 over 1 plus x whole squared is 1/4. But we notice that that series is equal to minus 3c. If minus 3c is 1/4, c must be minus 1/12. So this is Ramanujan's proof of this statement. Okay. Now, the remarkable thing here is that you can think of, if you look at the Riemann zeta function, zeta s is summation 1 over n to the s, for real part s bigger than 1. As a series, this is convergent only in the half plane, real part s bigger than 1. But we all know that Riemann's functional equation permits an analytic continuation of this function to the entire complex plane, and that in doing so, you end up with a function which is analytic everywhere except at one point s equal to 1, where it has a simple pole. Now, if you use this analytic continuation using Riemann's functional equation, and if you think of zeta of minus 1 formally to represent 1 plus 2 plus 3, etc., and it uses this thing for the analytic continuation, it turns out that the value minus 1/12, which you may not see at the bottom of the slide because there is something there about google.com that I see on my slide, it turns out that zeta minus 1 is minus 1/12. And that's what Ramanujan is asserting for this series. So what is amazing about this is that Hardy said Ramanujan did not understand complex variable theory and analytic continuation, but then how did he arrive at the correct value for zeta of minus 1? By doing this formal manipulation without any analytic continuation. So what is interesting here is that Ramanujan had his own theory called the theory of constants. So for every series, convergent or divergent, he would associate a constant to that series. He called it a constant of the series. And the constant associated with this series is minus 1/12. Now let me make one comment here which is not on the slide. We all know that the zeta function has zeros at the negative even integers, minus 2, minus 4, minus 6, etc. If you use this crazy method of Ramanujan and evaluate minus 2, zeta of minus 2, you will actually get 0. If you use this to evaluate zeta minus 4, it's 0. So all the zeros of the Riemann zeta function at the negative even integers can be predicted by Ramanujan's method. So crazy as it seems, it always gives this correct answer. So this is related to Euler-Maclaurin series, of course. Now I just want to make a comment here about Abel, because I said I'll make comparisons. So Abel also lived only for about 27 years. And like Ramanujan, his life was full of impediments due to poverty and in case also ill health. But like Ramanujan, he made revolutionary contributions. Abel and Jacobi simultaneously and independently discovered elliptic functions. Ramanujan learned elliptic functions on his own and had his own theory of elliptic functions. Now, Abel also investigated infinite series in great depth and is supposed to have made a statement: divergent series are the invention of the devil, and it is shameful to base on them any demonstration. Very interestingly, Ramanujan was basing his demonstration on certain manipulations of infinite series, which formally are okay, but in a rigorous sense are not valid. Yet, it always gave the right value for the series. Very interesting. All right. So now let me also just make one comment that Abel is worshipped in Norway like Ramanujan is worshipped in India, justifiably so. So the famous Abel Prize was instituted for the 200th birth anniversary of Abel. And I will say Abel is to Norway what Ramanujan is to India. So I would say that even though with the prize money is not the same, now the prestige is increasing. The Shasta Ramanujan prize is what we have now brought in for Ramanujan. Let me make a comment about Galois, because Hardy made this comment comparing Ramanujan with young, brilliant people like Abel and Galois. Galois, of course, also died very young, much younger than Abel. He died at the age of 20. And he, of course, revolutionized mathematics by talking of the group concept when solving polynomial equations of degree greater than 5. He was looking at the various mappings, which are these automorphisms between fields. But he died a tragic death in a duel. So I don't want to get into the story of Galois, except to say Galois also wrote a letter to his friend one day before he died. And that is really what has now become Galois theory. So compare it with Ramanujan's last letter to Hardy, written from his deathbed, in which he communicated the Mach theta functions.
Professor Aladi, so
Yes.
you can hide that tab which coming google.com. So there is a hide.
I just hit the word hide.
Yes.
Okay.
Yes.
But later you have to tell me how to do the stop sharing, okay? Anyway, all right. So now let me say something about Riemann and then we'll get back to Ramanujan's mathematics. Hardy said that the real tragedy with Ramanujan's life was not his early death, but that in his most formative years, he was distracted and a lot of his work was rediscovery. He may have been wrong in this. I'll make a comment about this with regard to Mach theta functions later. So the four mathematicians whom he quoted were Galois, Abel, and Riemann. Riemann dying at the age of 40. And he said they had all done their greatest work by then. Of course, the Riemann hypothesis is his only paper in number theory. It's an 8-page paper. And the point here is that regardless of whether Ramanujan understood analytic number theory or not, he actually did some very interesting things on values of the Riemann zeta function. He even had formulas for odd zeta, zeta 3, zeta 5, and so on. Of course, they are not leading to irrationality proofs, but he had some interesting formulas. All right, now let us move to some mathematics. Yeah, back to mathematics. We'll talk about partitions. The partition of an integer is a representation of that integer as a sum of other positive integers, two representations considered the same if they only differ in the order of the parts. So for instance, 2 plus 1 plus 1 is the same partition of 4 as 1 plus 2 plus 1. So we may write all the parts in a preferred order, and we usually write them in descending order. Now, the number of partitions of a small number like 4 is easy to compute because you can write down all the partitions. But writing down the partitions of 200 is impossible because there are actually 4 trillion partitions of nearly 4 trillion partitions of 200. Euler was the founder of the theory of partitions, and he noticed that there are very beautiful product representations for certain generating functions. In particular, the generating function for the partition function P of n is this product 1 over 1 minus q to the m from 1 to infinity. But what is most interesting is if you take the reciprocal of this partition generating function, which is the product 1 minus q to the m from 1 to infinity, you can actually explicitly write down the power series and the coefficients. Almost all the coefficients are 0. The only exceptions are the coefficients of the powers of q, which are pentagonal numbers, 3k squared minus k over 2. And even there, you can exactly determine what the coefficient is. It's plus or minus 1. It's minus 1 to the k. The nice thing about this is, if you multiply the two products, 1 over 1 minus q to the m with product 1 minus q to the m, you get 1. Which means if you multiply the pentagonal series with the summation p and q to the n, you get 1. So if you compare the coefficients, you end up with this remarkable recurrence formula for P of n, that P of n is P of n minus 1 plus P of n minus 2 minus P of n minus 5 and so on. These numbers 1, 2, 5, 7, 12, 15 are the values of the pentagonal numbers. So this is a remarkable recurrence formula for Euler. Now, this is a statement I'd like to make. The theory of partitions was founded by Euler, but even though partitions are combinatorial objects, Euler never used combinatorial techniques. He only used power series techniques. The combinatorial influence in partitions is due to Sylvester. So that is the end of the 19th century. And I like to say that Ramanujan's magic touch gloriously transformed the subject. So he and Hardy collaborated using an analytic method to evaluate asymptotically the number of partitions of n. And I will come to this comment of Selberg in a moment. So the whole idea is, if you think of P of n, q to the n, as an analytic function of q in the unit disk, call that function f of q, then if you use the Cauchy residue theorem and do the contour integral f of q over q to the n plus 1 dq over a suitably chosen contour, this will give you the value of P of n. So this is simple. However, the real difficulty here is in choosing this contour and making the estimations accurately or with great care. So if you look at the product there, you see that it blows up when q is 1. It blows up when q squared is 1, when q cubed is 1, and so on. So it blows up at all the roots of unity. So the whole idea is you choose a circle first. You choose a circle within the unit circle, and then you deform this circle to go close to these roots of unity to pick up the contribution near these roots of unity. And that is how you end up with this asymptotic formula. So I've just written this down in somewhat simpler terms. There is a leading term, P1 of n, then there is P2 of n, etc. I've given the formula for Pj of n. It's an Lj of n times Pj of n, but Lj is a finite sum involving the 24th roots of unity, and Pj of n is this expression which involves the exponential function. The values are given here. Lambda n is n minus 1 over 24, and the constant k is pi times square root of 2 over 3. So if you take j equal to 1, the leading term that you get here is e to the power pi times square root of 2n over 3 divided by n. Now, this leading term, it's possible to get this by simple elementary calculations. Elementary doesn't mean easy. You have to spend 15 to 20 minutes to actually write down the proof that this is the leading term. This is possible, and I do this for my graduate class. I give this as also an exercise, giving them some hints. Now, what is more remarkable is this expansion. So the question is, what was Hardy's contribution and what was Ramanujan's contribution on this? Not much is written about this because Hardy had this view that if two people collaborate, they are equal. You should never ask who did what. You should never say contribution of A is more important than the contribution of B. This is actually one of the greatest practices in mathematics. This is not the case in the other sciences. In physics, there is a first author, and there are a bunch of authors below that person. In mathematics, all authors are equal. So Hardy never said who did what in his collaboration with Ramanujan. So how do we know who did what? Read Littlewood's report about this. And basically, what Littlewood says is, it is Ramanujan who conjectured how these roots of unity enter into this calculation and what the contribution at these roots of unity will be. So this formula like ddn, e to the k lambda n over j lambda n, that is a Ramanujan intuition. However, somebody had to establish this rigorously, and Hardy, with his analytical skills, with his mastery over all these techniques, was able to show how to deform the contour, how to use the Faraday dissection of the circle, and get this asymptotic formula. So Littlewood actually tells you what exactly each person did. So really speaking, the genius of Ramanujan combined with the technical prowess of Hardy was what led to this result. So both of them deserve credit, but I'm telling you exactly how this happened. All right, but now Hans Rademacher. Now, okay, word about this Hardy-Ramanujan series. This series is not actually convergent, infinite series. It's divergent as an infinite series. However, if you truncate this infinite series at a certain point, which is about the order of magnitude n to the 1/2, the value that you get, its nearest integer, will be P of n. In that sense, this is genuinely an asymptotic series. Now, what Rademacher did was he replaced the exponential function. This is a little bit simplified version. He did other things. He replaced the exponential function by this hyperbolic function. And then he converted that series into an infinite series, whose value converges to P of n. This is quite remarkable. So nowadays, in many courses, people don't do the Hardy-Ramanujan series. They directly do the Rademacher series, because that replacement of the exponential function by the hyperbolic function does the job for you. Now I want to make a comment here about what Selberg said about this. So this was during the Ramanujan centennial in Madras on December 22nd, and Arthur Selberg was giving this lecture right after the lecture of Subramaniam Chandrasekhar, the Nobel laureate. So Selberg said he too started investigating a formula for P of n, and he directly arrived at the Rademacher result. But once he found out that Rademacher had published this, he lost interest and did not publish it at all. But the comment that Selberg made was, the Rademacher series is actually more natural compared to the Hardy-Ramanujan asymptotic series, which doesn't converge but has to be truncated to yield the nearest integer value, nearest integer of which is P of n. Apparently, Ramanujan was insisting that there is an infinite convergent series, but he could not pin down what exactly it is. And Hardy thought an infinite convergent series to P of n is too good to be true, and consequently settled for less. And Ramanujan, out of respect for his teacher, did not argue with him, and therefore both of them settled for this asymptotic series. So Selberg was somewhat critical about Ramanujan, and there he made a comment. Look at that letter that Ramanujan sent to Hardy. In that letter, there is this comment about the hyperbolic function and the exact formula. This is similar to what Rademacher's formula is. So this was Selberg's comment in the Ramanujan centennial. Anyway, the method of Hardy and Ramanujan has been vastly generalized by Hardy and Littlewood in a series of papers under the title Some Problems in Partitio Numerorum, and this has been applied to a whole class of problems in additive number theory. All right, now let me come to partition congruences. Major McMahon, the great combinatorialist, was asked by Hardy to compute the value of P of 200 using Euler's formula. You remember that recurrence relation? And that formula must also be compared with what P of 200 is given by the asymptotic series. And it turned out it was both of them gave the same values. It was a verification of the formula. But now what McMahon did was, in that process, he formed a table of partitions, P of 1, P of 2, etc. Now, Hardy showed this table to Ramanujan. Ramanujan took one look at this table and immediately wrote down these three congruences. He never expected that a partition function which is defined by an additive process was able to arrive at the first congruence was the way McMahon prepared the table. This is how McMahon prepared the table. So he had P of 1, P of 2, P of 3, P of 4, P of 5, P of 6, and so on. So the partition function values of the multiples of 5 were all available at the last row. So if you took a close look at the last row, you could see that they're all multiples of 5. So you could arrive at the first congruence. Okay. What about P of 7m plus 5? That's not so obvious. What about P of 11m plus 6? That's also not obvious. So it's one thing to say that if I had been in Ramanujan's position and seen the table, I could have located the first congruence. I don't think so. An individual must have the eye to spot certain things. Just because some astronomer becomes famous because he has spotted a certain galaxy or a star. You can say, if I was behind the telescope, I could have discovered that. Not really. You should know what you're looking for. Ramanujan knew what he was looking for. McMahon prepared the table. He didn't discover this congruence. Hardy checked the table. He did not discover the congruences. Ramanujan wrote down the congruences as soon as he saw the table. But Ramanujan went further. Not only did he state the congruences, he wrote down this remarkable formula for the generating function of P of 5n plus 4. And you see the constant 5 sitting outside. So clearly, every coefficient is a multiple of 5. He also wrote down a similar identity for P of 7n plus 5, the generating function for that. And you see that it has coefficients which are multiples of 7. Actually, you can use these formulae to show that P of 25n plus 24 is a multiple of 25, and P of 49n plus 47 is a multiple of 49. So you can prove stronger congruences modulo 5 squared and 7 squared from these two identities of Ramanujan. Now, let me move to another topic, a very famous topic called the Rajab-Ramanujan identities. So these identities were discovered by Ramanujan sometime before his departure from India, because he communicated them in his letters to Hardy. He did not actually communicate the identities themselves. He communicated the fact that the ratio of the two series expands as a continued fraction, and that continued fraction leads to an infinite product. These identities were actually proved by L.J. Rogers, a British mathematician who was actually very similar to Ramanujan in his tastes in Q series, but did not get the recognition. It was only later, after Ramanujan arrived in England, when Hardy asked Ramanujan, how do you prove these identities? And Ramanujan said, I don't know how to do this, but I know the identities are true. Ramanujan bumped into a trilogy of papers of L.J. Rogers in the London Math Society, where these identities were proved and much more. And rather than feeling jealous, he praised Rogers for the proof of these identities. And that is why Rogers became famous in England. So we in India, we criticize other Indians, our Indian group, by saying we don't recognize talent unless they are recognized by people outside. Well, what happened in England? They never recognized L.J. Rogers until Ramanujan spotted Rogers' paper and said, he has proved these identities. This is remarkable mathematics. So it happens in other countries. Now, these identities have partition interpretation. This is actually due to McMahon and Shore. The first identity says that the number of partitions of an integer into parts that differ by at least 2 is equal to the number of partitions of that integer into parts congruent to plus or minus 1 mod 5. The second one has a similar interpretation, but with the fact that all parts are at least 2. So the point here is that if you take the ratio of these two series, you end up with this continued fraction that I have here. And what Ramanujan is doing is evaluating this continued fraction as e to the minus 2 pi over square root of 5, which is what you saw in the earlier slide. So what he communicated in his letter to Hardy was the value of this continued fraction as obtained from putting q equal to e to the minus 2 pi over square root of 5 in that product. So that is what he was showing Hardy. Now this theory has actually blossomed into a very broad subject where we look at partitions with difference conditions on the one side and congruence conditions on the other. In fact, my own research in this area is in classes of such identities which are called Rogers Ramanujan type identities. But I don't want to get into my own research except to say that I have worked in this area for more than a decade. All right, let me move on to another paper of Ramanujan, which did not make a splash in the beginning, like his famous paper on the partition function with G.H. Hardy. So we all know about the sequence of primes being infinite. And what is very interesting is that although prime numbers have been investigated since antiquity, the first systematic investigation of the number of prime factors is due to Hardy and Ramanujan, which is very recent compared to the long history of number theory. They both wanted to explain the phenomenon round numbers are rare, where a number is round if it is a product of a large number of small prime factors. So for instance, 81 is round, although we don't think of 81 as round. If you write it to base 3, it is 10,000. So it's definitely round. So we have two measures of roundness. We can either consider a measure being the number of distinct prime factors of n, or the total number of prime factors of n. And it turns out that the two measures are more or less the same, and that is Theorem Hardy-Ramanujan 1 at the bottom, where the log n is the average value for both the prime factors counted with multiplicity and the prime factors counted distinctly. But now what is important in the Hardy-Ramanujan paper, that they make this observation that most arithmetical functions are well behaved in terms of their average. But the average does not tell you what is happening most of the time. Sporadically large values will influence the average. So they introduce the concept of normal order. So we say that an arithmetical function f of n has a monotone function g of n as a normal order. If for every epsilon bigger than 0, the limit x tends to infinity, n epsilon of x over x is 1. But n epsilon of x is the number of integers for which the ratio f over g at value n lies between 1 minus epsilon and 1 plus epsilon. So we are basically saying f of n and g of n are about the same asymptotically almost always. So the remarkable theorem of Hardy and Ramanujan is that both omega n and capital omega n have log n as the normal order. So this is a correct measure of roundness. Now, how did Hardy and Ramanujan prove this? Very interesting proof. They look at what is called the local distribution, omega sub k of x, the number of integers up to x for which omega n is equal to k. And they obtain a uniform upper bound for omega k of x, which I have described here. Notice, this is like the Poisson distribution, right? So if you show that the tail of the Poisson distribution is insignificant, then we prove that almost all numbers are clustered around the center. That proves your almost all result. So the whole idea that is needed now is to show that summation c to the k over k factorial, where the c is deviant, is away from k by a quantity more than c to the half plus epsilon. So that contribution compared to the full series, which is 1 over e to the c, if that is 0, then that proves the almost all result, because that tells you that almost all numbers will have the number of prime factors log x with deviation about log x to the half plus epsilon. So this they established by induction. Now, this actually led to a very beautiful theorem in 1939 called the Urdish theorem, where actually probability was infused into the subject. What this theorem says is that if you ask for the probability that omega n minus log x is less than lambda square root of log x, That probability is the area under the Gaussian curve from minus infinity to lambda. So this is the Urdish-Cox theorem. Here is a fantastic collaboration between Mark Cox, a probabilist, and Paul Urdish, who is a number theorist. I do not have time to get into the story of the Urdish-Cox theorem. It's a remarkable story in itself. Okay, for anybody, if they want to know, they can ask me a question later and I will briefly tell what the story is. All right, so now, the subject of probabilistic number theory is a very thriving subject today. We discuss additive functions in general, multiplicative functions and so on. In fact, before I was inflicted by the Q disease, as Professor Ramakrishnan said, I was actually working in probabilistic number theory, and one of the things I established was an Urdish-Cox theorem for smooth numbers, and that paper appeared in Acta Arithmetica in '88. That is just an example of one of the results that I had established. Anyway, now let us come to this taxi cab number, and I want to say something about this, which not everybody might know. Now, what everybody knows is that Hardy arrived in a taxi numbered 1729 at a hospital when he was there to call on Ramanujan, who was ill. And as soon as he mentioned this taxi number, Ramanujan immediately said, it's 10 cubed plus 9 cubed equal to 12 cubed plus 1 cubed, and Hardy was stunned. Yes, that is true. Now, the point here is this. Think of the equation as x cubed plus y cubed equal to z cubed plus w cubed. And I can rewrite this as x cubed plus y cubed plus z cubed equal to w cubed by replacing z by minus z. Now, there are solutions to this. We all know 3 squared plus 4 squared equal to 5 squared. But not many of us tell our school children 3 cubed plus 4 cubed plus 5 cubed is 6 cubed. Isn't that just as beautiful as 3 squared plus 5 squared equal to 4 squared equal to 5 squared? But we never tell our children this. So this is a solution to a Ramanujan type equation. Now, Euler actually solved this equation x cubed plus y cubed equal to z cubed plus w cubed. So this is really should be known as Euler's equation. Now, Ramanujan also found a class of solutions to this equation by parametrizing them. And I have got that at the top of the slide. That's a parametrization of x, y, z, and w. You can choose a, b to be any values. Plug them in. Compute the corresponding x, y, z, w. You will get a solution to x cubed plus y cubed equals z cubed plus w cubed. Now, the interesting thing is, Ramanujan had solved this in India before he arrived in England. So when Hardy showed him the 1729 number, immediately Ramanujan remembered that this number was one of the things that he had found in India. That's why he immediately told Ramanujan to Hardy, yes, this is an example of a number which can be written as a sum of 2 cubes in 2 different ways. But he never told Hardy that he had worked on it before. Another example of how Ramanujan liked to shock people. All right. So now Fermat, like Ramanujan, wrote letters communicating his findings. Now, the Fermat equation is a special case of the taxicab equation with the exponent 3 when you put w equal to 0. But if you put w equal to 0, you also get all other solutions to be trivial. In principle, you could say maybe Ramanujan had solved Fermat's equation for cubes. In any event, Ramanujan was never really interested in Fermat's equation in general, but I made a comparison with Fermat. All right, so now let us move on to Mach theta functions, and this is my last mathematical topic. So now, what is it that I have here at the bottom? What I have here at the bottom is, remember the partition generating function that I had? If you take the partition generating function, that will be q over 1 minus q, q to the 4 over 1 minus q squared, q to the 9 over 1 minus q squared, 1 minus q cubed. If you just change the minus signs to a plus sign, like I have done here, you get Ramanujan's Mach theta function of order 5. Now, Mach theta functions are a great topic of discussion today, and I want to just say a little bit about the current state of Mach theta functions before I get back to some things relating to Ramanujan. So, should I now press escape? Hello?
Yes, you can press escape.
Yes, sir.
Yeah, I press escape. All right. Now, I will minimize this. And now can I go to the other one?
Yes.
Hold on, I'm getting all sorts of interruptions here. See, I'm getting these things. I don't need all this. Okay, it says I'm presenting everyone. I know that. All right. So the 2009 Shasta Ramanujan Prize was given to Catherine Brinkman for outstanding work relating to Mach theta functions. So there has been a revival of interest in Mach theta functions after Ken Ono and Catherine Brinkman have worked on it, and now a whole group of people are working on Mach theta functions. As they say in America, this has become a cottage industry. So what are Mach theta functions? Mach theta functions are like classical theta functions in the sense that their coefficients can be calculated to a degree of precision, like the coefficients obtained for products represented in terms of theta functions, like the partition functions. But they are not classical modular forms. So no one knew how exactly to connect theta functions with Mach theta functions. So that was done by Sanders Weggers as a PhD student under Don Zagier. And Brinkman and Ono followed the lead of Sanders Weggers to obtain this key to unlock the Mach theta functions. Okay, so I'll go to the next slide where I explain this. So there it is. So here is the point. Weggers rewrote Mach theta functions in terms of certain Lambert series, indefinite theta series, and showed exactly how Ramanujan's Mach theta functions fit into this theory. So the next slide will tell you something about this. So what is a Mach theta function? It is an expression of the form f plus f minus, where f plus is a holomorphic part and f minus is a non-holomorphic part. The holomorphic part is a modular form with weight 1/2 or 3/2, and the f minus is an integral involving, now the weight is either minus is 3/2 is now replaced by 1/2 and 1/2 is replaced by 3/2. It is what is called a unary theta function. So this is the modern definition of the Mach theta function. And what Brinkman and Ono showed was all 22 of Ramanujan's Mach theta functions fit into this classification of fit into this definition, modern definition of the Mach theta function. But there are objects which fit into the modern definition of the Mach theta functions, which are not Ramanujan's definition of a Mach theta function. So this is a broader class. That's the big advance. Okay, so I give a reference here to a paper of Brinkman, Folsom, Ono, and Larry Rowland. But now I will say something more. What is Ramanujan's definition of a Mach theta function? It's not really very precise because it is written in this letter to Hardy. He didn't write a paper on it. So he says it is a function which satisfies certain conditions, that it can be written in an Eulerian series. That means q to the power quadratic function like an n squared or 3n squared or something. And as you move radially to a root of unity on the unit circle, you get certain limits. But the limits won't be the same along, it's not a single theta function which gives you this limit radially. So it is somewhat of an imprecise definition, but now people understand this more precisely with this more general definition. So here are the examples of Mach theta functions that I have. So if you take q to the n squared and put z equal to 1, that is the generating function for the partition function. This here with the z is the generating function for Dyson's rank. Now if I put z equal to -1, I get the generating function for Ramanujan's fifth order Mach theta function. Let its coefficients be called alpha n. Now you have the Rogers-Ramanujan identities, that is, which can be written using Jacobi's triple product identity in this form. But now the fifth order Mach theta function comes by replacing plus by minus. But now why do I bring this in? I bring this in because there is a very famous conjecture of George Andrews and Dragonet, which says that, like the partition function, there ought to be a Rademacher type formula for alpha n. Such a formula was found by Brinkman and Ono. So the reason I brought up this particular slide is I wanted to show that the theory of Mach theta functions is alive in today's world. I'm getting this interference presenting something, and I know that. I don't want that interference. Okay, so now wait, I'm supposed to get this. Yes. I should do full screen. Hold on, I'll do it in a moment. All right, so yeah, are you able to see this now?
Yes, yes.
Okay, now I move down to other things. So here is the Wren Library in Cambridge University, where George Andrews discovered the lost notebook of Ramanujan, and he recognized it because he had worked previously on Mach theta functions. And he saw this whole set of identities on Mach theta functions written in that set of sheets. Okay, now in the last 5 minutes, I'm going to tell you about what has happened in the world of Ramanujan in terms of preservation of Ramanujan's legacy. We know that 1987 was the Ramanujan centennial, when mathematicians around the world gathered in India to pay homage to the genius. That's when the lost notebook and other unpublished papers were brought out in a printed form by Springer and Narosa, and a magnificent foreword to this was written by George Andrews. It was a year later that Robert Canigal visited India and came out with this book some years later, which is now such a well-known book. In fact, it is this book which is given as one of the prizes for the Ramanujan math contest in Mauritius, and probably it should be given to high school students in India on a regular basis. This has now also become a basis of a movie. And I want to tell you, those of you who have not seen the review, please see my 17-page review of this movie, The Man Who Knew Infinity. I have praised it a lot, but I've also criticized it for areas where there has been unnecessary exaggeration. So if you have the time, please read my detailed review. Shasta University is, I think, a major figure in the world of Ramanujan. It was formed some 2 decades back. It has really grown by leaps and bounds. Its main campus is in Tanjore, but they opened a branch campus in Kumbakonam also in 2000, and in 2003 they bought Ramanujan's home and they are maintaining it as a museum. In 2003, Abdul Kalam, the President of India, inaugurated the first Shastra conference, and that is how I got involved with Shastra. And he opened this home and said that this is a museum. And a decision was also taken in 2003 to conduct these conferences annually, and Shastra asked me to help them conduct these conferences. So that's why I go annually to Kumbakonam. It's like a pilgrimage to me. So this is Srinivasa Ramanujan's home with Shastra's name on it. The only change they made, remember I showed you that main room of Ramanujan. What they have done is to add this statue in the middle. So that's the first conference, and I had the pleasure of being introduced to Abdul Kalam. Right next to me is George Andrews, and next to Andrews is Noam Elkis of Harvard University. They have one of the finest Ramanujan museums there. So there you're seeing me with my wife Mathura in the Ramanujan Museum. It's worth visiting. And this is in the central courtyard of Shastra with the Vice Chancellor Sethuraman. So the Shastra Ramanujan Prize was instituted in 2005, but the decision to create the prize came in 2004 at a conference where they asked me to inaugurate. And as I was going up to the dais, the Vice Chancellor said that he had he wants to give $10,000 annually for a cause of Ramanujan, and asked me to announce right there, without consulting any committee, how this $10,000 has to be used. So I immediately said, give a prize in the name of Ramanujan for mathematicians not exceeding the age of 32, because it's a challenge for them what they can do in the same lifespan, in the same time span of Ramanujan's life. So as you know, the first winners of the prize were Bhargava and Soundararajan. They had 2 full prizes, not shared. So here's a picture of Bhargava and Soundararajan receiving the prize. And by the by, when Bhargava gave his talk, he spoke about a solution of a famous problem of Ramanujan on quadratic form. Unfortunately, I don't have time to go over this here. If somebody has a question, of course, I can show some slides. So here are some pictures of mathematicians who have visited Kumbakonam. Ken Ono comes there every other year. There you see him, third from the left. Right next to him is James Maynard, who won the prize in 2014. And on the right. So those of you who have not looked at it, I would like you to look at the 5 volumes of Bruce Bundt, for which he got the Steele Prize. And more recently, the 5 volumes of Andrews and Bruce Bundt on Ramanujan's Lost Notebook. I want to advertise my own book, Ramanujan's Place in the World of Mathematics, which was released in 2012 for the 125th anniversary of Ramanujan's birth. The second and enhanced edition will appear in 2021. Of course, the Ramanujan Journal was launched in 1997, and now it started as a journal with 1 volume of 4 issues of 100 pages, and now we publish 3 volumes of 3 issues each. Each issue is 250 pages, so it has become 5 times the size. I'm not talking about size as a measure of quality, but size also indicates here that the wealth of papers that are flowing in. So here's our editorial board at one time. So I will just like to, and now I'm involved in this Ramanujan encyclopedia. I do not know when it will appear. It may take a few years, but quite a few people are contributing. The main editors are, besides me, are Andrews, Bruce Bundt, and Ken Ono, but we have included now 4 more editors, associate editors, Peter Pauli, Asia E, Ole Warnar, and Frank Garvin, my colleague. And it's proceeding slowly, but the derivative is positive. So the concluding thought is that, it's now more than 125 years since Ramanujan has died, but his influence continues to grow. Some of you may want to look at this article in the Notices of the AMS, which appeared in 2013 January, which talks about all the progress. And Hardy felt that the tragedy of Ramanujan was not his early death, that he had already done his best mathematics. But I think he may have been wrong in this, and so does Bruce Bundt and George Andrews. Because when he was doing his Mach theta functions, he was still rising as a mathematician. So he may actually have been wrong in this estimation. So I just want to conclude with 2 quotes, mine and Freeman Dyson. The opening issue of the Ramanujan Journal, I said, the very mention of Ramanujan's name reminds us of the thrill of mathematical discovery. Freeman Dyson said, we should be thankful to Ramanujan, not only for discovering so much, but giving others the opportunity for discovery. By that, he means he never gave full proofs. So he gives you the pleasure of giving you the proof and discovering something more. So with that, I'd like to stop. Thank you so much for your attention. Let me minimize this. And I'd like to express my thanks for asking me to give this talk.
Okay, thank you very much, Dr. Alladi, for giving an excellent exposition of Ramanujan's works. We have covered almost everything of Ramanujan's works. So now, if there is any question, I think I request the audience to ask. Please mute your, all others please mute, because it is echoing.
It is really a very interesting talk and very illuminating and thought-provoking talk by Professor Alladi. I welcome Professor Alladi whenever he is coming to India. Let him visit to IIT BHU. I invite him.
Thank you.
Any other question or comments?
Yeah, hi, can I say something?
Yes, Sudhir.
Yeah, hi, Krishna. Thank you for this wonderful talk. I just wanted to ask you if it is possible to share the slides of your talk with me or with maybe a broader audience.
Sure. Yeah, I mean, when I gave this talk at IIT in Gandhinagar, I think it was Atul Dixit and Vivekananda Maji asked for the slides, and I gave it to them, and I'm more than happy to give these to you. No problem.
Okay.
As I said, the slides are a little bit more rudimentary, and I gave it to students.
Sure.
But you will still find it useful for students.
Yeah, yeah, it's a good.
Yeah, sure, no problem.
Yeah, thanks again, and good to see you.
Yeah, same here.
Any other questions or comments?
Sir, it
So
has
can you
been
tell us
always, sir, it has been
sorry.
always a very good pleasure for us to listen to you again, sir. Thank you.
Thank you. You know, it's 10:30 p.m. It's 11:30 p.m. for me. 10:30 to 11:30. And I get up. I'm going to get up at 4 in the morning, and I have to chair the session. I mean, you can still continue. I'm not saying I'm going to sleep now. I have a talk in the morning of Shai Evra, the Shasta Prize winner, at Indian Standard Time, which is 8 a.m. my time.
Can I
Okay.
ask a quick question?
Yeah, please.
Yes.
Yeah. So can you tell us the story of Erdos and Kaas and how the theorem came about?
Okay, so I won't get back to the slide because it's a complicated process. So I'll tell this to you briefly in about 2-3 minutes maximum. So Mark Katz, a great probabilist, this lecture at Princeton University. And the title of the lecture was Some Applications of the Theory of Probability to Analysis and Number Theory. So he was giving different types of applications. So basically what he was saying was, when you take an interval from 1 to x, the probability that an integer is a multiple of p is 1 over p, roughly. Not a multiple of p is 1 minus 1 over p. The probability it's a multiple of q is 1 over q, not a multiple of p. Q is 1 minus 1 over q. But these probabilities seem to be nearly independent. So he said, what if I have a model in which I have random variables which take value 1 over p, which take a multiple of p with probability 1 over p. These random variables are completely independent, identically independent random variables. There a way in which you can compare the two models, and if you do, you can use the central limit theorem and arrive at such a result. So Katz actually thought of such a result, but he did not know how to do this. All Urdish was in the audience. So when the lecture was over, he went up to Katz and said, I know how to do this. This is the whole idea behind Brun's sieve. But the problem with Brun's sieve is the asymptotics works only if you sieve up to a point y equal to x to the epsilon, where epsilon tends to 0 as x tends to infinity. You can't sieve up to x to the 1/2 or x to the 1/3 and get the same asymptotic. So Urdish said, you first establish this theorem for the truncated additive function, where instead of f of n, you sum only the values of a primes up to p less than y. Then you fill the gap between f of n and fy of n by what is called the Torsion inequality. That is how this theorem can be proved. So that is how the Urdish-Katz theorem was proved. But as Urdish said, 2 brains are better than 1. I did not know probability, and Katz did not know sieves. But we each knew the subject that we were working on. So we collaborated, and the Urdish-Katz theorem was born, and probabilistic number.
Okay, if there are no more questions, we thank the speaker once again. Thank you, Krishna, for giving wonderful lecture in this conference. Okay.
Thank you.
Akash, there is a raised hands. You can say.
Yeah. No, that Ankush has asked.
You can raise the hand. Yeah, something like that.
Yeah, thank you.
Okay, thank you.
All right. So
Now
can I leave the meeting, or
yeah,
I can leave the meeting?
Yeah, if you want, you can.
Yeah. Yeah.
Okay. Thank you, guys.
Okay, thank
It's been a pleasure. It's been a pleasure. Thank you.
Thank you.
So how do I leave the meeting?
Yeah, just there is a
Leave. There is a leave meeting. There is something.
Yeah.
All right. Do I just completely
You
put
can just press the power button off, like the phone button.
I'll press the X or something.
There's a red phone button
Phone button.
in the middle.
Oh, yes.
Yeah. Just
Yeah.
click on.
Okay.
Okay, thank you. So I thank you, Professor Ramakrishnan, to chair this session. Now I would like to request Professor Vrindavan Sahu to chair our next session. Over to you, sir.
Okay, good morning to everyone. I'm happy to introduce Professor Michael Griffin. Michael Griffin completed his PhD in 2015 from Emory University, USA, under supervision of Professor Ken Ono. And then he was NSF postdoc at Princeton University and University of Cologne, Germany. Currently, he is at Brigham Young University, USA. He works on number theory. In particular, he has contributed significantly in automorphic forms, moon sign, elliptic curves. So let's listen Professor Michael Griffin on talk class pairings and elliptic curves. You're welcome, Griffin.
Okay. Thank you very much. Let's see.
So there is an option called present now. You can see.
Yeah, let's see. Present now.
Yeah, you click on that. So there is option share entire screen.
Yeah, there we go.
Yeah. So now you can.
Okay. Okay. Great.
Yes. Yes.
There we go. Okay. Is that visible to everyone?
Yes. Yes.
Okay. Great. Thank you so much, and thank you to the organizers for inviting me to meet with you and to speak today. It's always an honor to meet. I love visiting India. I wish that I could be there with you in person. It's one of my favorite places, and I have a great love for the mathematics of Ramanujan. The work that I'm going to be talking about today is a little bit different from my normal work. I often work on modular forms and harmonic Moss forms or Mach modular forms, and this work connects to that, but a little bit different than usual, a little bit less directly. The work that I'm going to be talking about today is not so difficult in some sense. It's I'll be talking about a lot of ideas that most graduate students, I think, well, not most graduate students, but many graduate students may have seen. And a lot of the ideas are not too difficult, but somehow they connect to some deep ideas that are, I think, very important and very interesting to me as I've been trying to understand how these ideas connect. So this work is joint with Ken Ono and Weilun Tsai. Weilun Tsai is a postdoc working with Ken Ono at University of Virginia. But what we're working on is connected to the theory of quadratic forms. And so I just want to briefly review some of the background on quadratic forms and their connection to elliptic curves, and eventually we'll talk about how these connect to the class group. So just as some background here, an integer binary quadratic form is just a binary expression like this: q of xy equals ax squared plus bxy plus cy squared with integer coefficients. And I'll be interested primarily in positive definite quadratic forms. So we'll have that a term to be positive and then a negative discriminant here. And so I may not always say that word positive definite, but throughout this talk, that's what I'm focused on. And then I'm also primarily interested in primitive quadratic forms. So I want these coefficients to have a GCD of 1. Okay. It turns out that if I've got an integer binary quadratic form, there is an associated ideal in the class group, or an ideal set up here. There's maybe a couple of different ways that you could do this. This ideal that I've given here is an order in the ring of integers of the number field q adjoin square root of the discriminant. Okay, but that'll play an important role here in a moment. We say that two quadratic forms are equivalent to each other if there's sort of a linear change of variable that transforms one of our quadratic forms into the other. And we ask that, so we'll do this kind of linear change of variable. We ask that those entries of the change of variable form a matrix, an integer matrix, in SL2Z, so with determinant 1, and that simply allows us that this is invertible by, again, an integer change of variable. It turns out that two forms are equivalent if and only if they represent the same integers. Okay? And that connects to some very interesting questions of representation of quadratic forms that Ramanujan and others have been very interested in. It turns out that this equivalence also tells us that those associated ideals that I had on the previous slide, they live in the same class, in the ideal class group. Okay? On the side of quadratic forms, we have a composition group law that allows us to sort of multiply classes of quadratic forms together, okay, to compose them to get a new quadratic form of the same discriminant, also an integer binary quadratic form. And it turns out that this composition law allows us to create a group on the quadratic forms that's isomorphic to the ideal class group for our discriminant, okay, for our quadratic forms. Okay. The class number is a number that's been very well studied. That's the size of this class group, or the number of quadratic forms for a negative discriminant, or classes of quadratic forms for a negative discriminant. Siegel proved that the size of this the class number is roughly the square root of the discriminant. And a little bit more precisely, we can adjust that by epsilon up or down, and then there are constants here that bound this class number. Unfortunately, the lower bound is completely inexplicit. The upper bound is very explicit. We've got a very specific description for an upper bound on the order of the square root of the discriminant. But that lower bound there is completely inexplicit, and is in fact connected to the question of the zero-free region of the Riemann zeta function. Okay? And so we don't have much hope at this point of being able to make that explicit without having some improvement, some real progress towards the Riemann hypothesis. Goldfeld and Gross-Zagier solved the problem of finding some effective lower bound. It wasn't anything close to what we expect to see there, assuming the Riemann hypothesis. Okay, where under the Riemann hypothesis we expect to see something on the order of the square root of the discriminant. They were able to show something that, say, Osterley was able to compile their work together and get this bound that's greater than something on the order of log discriminant. Okay, so much smaller than the square root of discriminant that we expect to see. But this was the first completely effective lower bound that could be proven. And this was proven, so Goldfeld gave a theorem that basically said there would be an effective lower bound if you could find an elliptic curve of rank at least 3. And Gross and Zagier were the first to provably find an elliptic curve of rank at least 3.
Oh, excuse me, Michael. So there is a question. Is
Yes.
minus d same as delta?
Oh yes, I think I've changed my notation here. So yes, I mean the discriminant of our quadratic forms. Yes.
Okay,
Yes. Thank you. Thank you for that. Yeah, and I'm sorry, I don't see the I don't have the view in front of me, so I can't see the question.
Yeah,
so
okay.
please feel free to interrupt.
Yeah,
if
okay.
Great. Okay. So now I want to shift gears just a little bit to talk about elliptic curves. Okay. So elliptic curves, okay, they'll have an equation for our purposes. I'm going to focus on elliptic curves with an equation of this form, where we've got y squared is equal to a cubic in x. Okay. And we're going to care about quadratic twists of an elliptic curve. Now this is not a standard form of the quadratic twist of an elliptic curve, but this is what we're going to look at. It's just a change of variable from the standard form for a quadratic twist. But basically we're just multiplying on the left by the discriminant here that we want to twist by. Okay. So now these elliptic curves here, we have that the points on these elliptic curves, they're related if you're looking over q adjoin the square root of d. Okay, there's a change of variables to go back and forth between those two equations over q adjoin square root of d, but not over just over the rationals themselves. Okay, and so the group of points on these two curves are, again, isomorphic if we're looking over Q adjoining square root of D, but generally they're not isomorphic. So generally it changes the group structure there a little bit. The theorem that we're interested in here is a map that connects the groups of elliptic curves, quadratic twist of elliptic curves, to a class pairing. So we're going to assume that we have an elliptic curve that has an integer equation, and we're going to suppose that delta is a negative discriminant and that it factors into little d times capital D. And that's a factorization of delta into discriminants. Okay. So, and one way we could do this, we could take one of these to be 1, for instance, to give a trivial factorization. Okay. Then what we have is there is an explicit map from these two twists of the elliptic curve. Again, we could take little d to be 1, and so that would be from our original elliptic curve across a twist. And then that maps to the class group of Q adjoin the square root of delta. Okay. And I'm going to describe that map explicitly below by giving a map from points on the elliptic curves to quadratic forms. Okay. So what we're going to do here is, assuming that I've got 2 points here, they'll have equations like this. We'll have an x coordinate a over c squared, y coordinate b over c cubed, and so on. Q is u over w squared, and then v over w cubed for those 2 coordinates. And we're going to create a quadratic form here. It's only really defined within an equivalence class. Okay, but we have these terms here. The alpha term here, that leading term, is going to look like this. Basically, what we're looking at here is the difference between the x coordinates of our 2 points, and then we've cleared to denominators. Okay. Then we want to divide by a GCD of some terms. Don't worry too much about all of that, but we'll need to clear out some of those factors. Primarily, just the difference between the x coordinates, and then clearing some denominators. Okay. The L coordinate here is an integer defined mod 2 times our leading term there. And what this should look like is little d times, and this right here is a ratio of the y coordinates of our 2 points. Okay, mod a factor of little d times alpha. And then it should be congruent to capital D times the reciprocal ratio of y coordinates here, mod capital D times alpha. Okay. And then finally, we should have that L squared is congruent to delta mod 4 alpha over G. So assuming that there exists such an L, okay, we should have that this quadratic form up here is, so the leading term there will be an integer because G divides alpha. If there exists such an L, then we have L squared minus delta is divisible by 4 alpha over G, so that final term is an integer, so this would be an integer quadratic form. And then with that final term there, it will have discriminant delta. Okay. So all we need to do to show that this makes sense is find or show that there exists some integer L that satisfies these nice properties here. Okay. And we'll come back to that in just a moment. Okay. Really quick, I want to talk a little bit about some of the history here connected to these ideas. So Buell wrote a paper on a similar type of map back in 1977. His was closely related to this, but he didn't allow for this factorization of discriminants. He assumed that basically we'd want little d to be 1, and then capital D then is the same thing as our delta, our discriminant. That needed to be the A6, so the constant term of the equation of the elliptic curve. Okay. And then our Q term needed to be a very specific point, basically this point 0, 1. Okay. In 94, Solang also wrote a paper on a similar map. His was a slight generalization of what Buell did. Okay. Once again, we have little d is equal to 1, so really just a single discriminant, no real factorization there. But then we've got a little bit of a generalization there for the second coordinate of the map. Okay. He did not describe this in terms of the second term n here being a point on the twist of the elliptic curve, but it's that's essentially what he was looking at. Okay. Pairing a little bit, or this map a little bit closer to what I've described here, is related to some work that I did with Ken Ono last year, and then on a couple of papers that we, along with Wei Lun Tsai, did this past year. And again, in all of those works, we've mostly focused on little d equaling 1. It simplifies some things, but we have this little bit more general map. As a follow-up to some of our work this last year, Ken Ono every year has a RU that does wonderful work and has some really fantastic results. This past year, he had a group of students work together on a project, and they considered, again, a little bit of a specialization here that they needed for the specific result that they were working on. But again, they were building on roughly the same map here. Okay. Buell, Solang, and then the RU show that their maps are linear, so that they give a homomorphism in at least one of the variables from the group of points on the elliptic curve to the class group. That was not essential to the work that I did with Ken and Wei Lun, and so we didn't bother proving that. The RU came back and they did need that for what they were looking at. Unfortunately, in order to get that, they need to impose a little bit of a condition on the second coordinate, which tells me that there's probably not optimal, the fact that we need this this restriction on the second variable to get the linearity. And this is a point of some ongoing research on my side to see if we can get this map to be completely bilinear. And there's reasons to believe that there should be a bilinear pairing kind of hanging around in the background. One of the main motivations for that thought is the fact that Buell and Solang's maps have been shown to be closely related to a pairing of Mazur and Tate that maps points on elliptic curve over number fields to, again, ideal class groups. And that pairing is bilinear. And it just happens that in the specific cases that Buell and Solang were looking at, okay, somehow this relates, the maps of Buell and Solang make the Mazur-Tate pairing very nice and explicit, much more so than the general description of the Mazur-Tate pairing. And so I believe that there's a way to make that explicit in a little bit more general sense than what Buell and Solang were doing. And I hope to be able to show that there exists a full bilinear pairing related to the Mazur-Tate pairing. In the meantime, let's come back and talk a little bit about the map that we had. So as I mentioned, in order to prove that theorem, we needed to show that there exists an L that satisfies those two properties. Basically, that's congruent to those ratios of y terms modulo various numbers. So what we're going to start with here is the equations of our points. So we know that P and Q live on their various twists of the elliptic curve, and therefore they satisfy the given equations here. Okay, so we have these two equations purely based on the fact that we know P and Q live on their respective twists of elliptic curves. Now we're going to take the difference between these two equations. On the right-hand side, okay, we can see that this clearly is divisible by, just algebraically, it's divisible by this factor a over c squared minus u over w squared, that difference in x terms. Okay. If we clear denominators, we end up getting that this piece here, basically the left-hand side with denominators cleared, is congruent to 0 mod this term that we called alpha. Okay, that was our alpha term in the description of the theorem. Of course, rearranging that, we get this this congruence, and if we essentially complete the square with this relation, we end up getting this expression here. If we complete the square in one direction, So here we're multiplying everything by little d, and then factoring out squares to the left. And of course, if we're dividing by things, we need to divide our modulus in order that makes sense. On the other hand, there's another way we could complete the square. We could multiply by a capital D, and then factor out squares on the right-hand side. Okay. Once again, so we get a modulus capital D times alpha, but then we have to divide by the pieces that we have to divide by a GCD with the pieces that we're dividing by on the left. Okay. So this tells us that these two pieces, their square is congruent to our discriminant delta, little d times capital D, modulo these two numbers here. Moreover, they're congruent to each other. We also have that their product with each other, okay, without the squares, is also congruent to, well, that's actually straight up just equal to little d times capital D. And so what we end up having here is that these two terms, okay, so inside the squares, those are congruent to each other modulo the GCD of those two moduluses. Okay? And that's what we need in order to get consistency, in order to do a Chinese remainder theorem argument to show that the L exists that we needed in our theorem. It is show that we have a well-defined map or that we've mapped to a specific integer quadratic form modulo the leading term. Okay. Great. So the question that we wanted to look at, given that we have this map from our pair of points on twists of the elliptic curves to the class group, okay, when do they map to different classes? And this is actually a theorem that Solang talked about, that he addressed, and but that was important to a larger question that we were interested in. So he gave a very nice description of this. Okay, so suppose that we've got these two quadratic forms. They have the same negative discriminant, and they have the given expressions here. Then we have that these quadratic forms here are equivalent to each other, that if they are equivalent to each other, then either the leading terms are equal, or the product of the leading terms is greater than the absolute value of the discriminant divided by 4. Okay? And that has to be the case if these two quadratic forms are equivalent to each other. It's not possible for them to be equivalent without either the leading term being the same or there being a little bit of a little bit of size on that leading term. And so basically, if we can look at quadratic forms with small leading terms that are different from each other, then we can show that those map to different classes. Okay. So suppose we've got these two quadratic forms that are related to each other by this linear change of variable. Okay, so they're equivalent. The leading term in this equality, on the left-hand side, you've got A2. That's the leading term of Q2. On the right-hand side, if you look at the leading term, that just comes from taking x equals 1, y equals 0. You end up getting the value of the quadratic form at A comma C. If C equals 0, then you just have basically that those leading terms have to be equal to each other because they both have to be positive. Okay. On the other hand, if C is not equal to 0, then we end up getting a relationship here. Completing the square, okay, we're able to find that this A2 has to equal 1 over A1 times this difference between a square and this factor with the discriminant. Okay. Now, we don't know what's inside the square. We don't know how big or small that could be, except that that's bounded by 0. That's really all we can say about the square. And so we know that this right-hand side here is at least the absolute value of delta times, so delta over A1 over A14. So here we're using that C is at least 1 if it's not 0. Okay, and we're using that delta is negative, so that negative delta is the absolute value of delta. Okay, And so again, just rearranging that, we end up getting that equality. A1 times A2 is at least the absolute value of delta over 4. Okay. So we wanted to use this idea to potentially count the size of, or at least give a lower bound to the size of the class group using counting methods for points on the elliptic curve. Okay. In order to do this, like I said, we need to produce quadratic forms with small leading term. And so for that process, we need to find points with small height. So we're going to talk about what that means here in just a moment here. Okay. So suppose we've got an elliptic curve with this given equation, and suppose that it has a rank R. Okay. Negative discriminant, negative fundamental discriminant is chosen so that there's a suitable point on the twist of the elliptic curve by -d. I'm not going to describe what the suitable point means. It's a little bit technical, but it's not really an important point for what I'm going to discuss here. So we'll just leave that in quotes here. But what we're able to find then is that our class number, h of -d, is at least this bound here. Okay. Now here on the left, we've got a lot of constants that are all completely explicit, and I'll explain what those are. And then there's a completely explicit error term that we can describe here. I'm not going to describe the error term today, but it is completely explicit. Okay, so in particular, we find that if we are able to work with an elliptic curve of rank at least 3, we beat the Gross-Zagier bound for the size of the class group. Okay. So this was the equation, or the inequality in our theorem. Okay, let's talk about what these constants are. Okay, so E tor of Q is the torsion subgroup. Okay, so the group of group of points of finite order on the elliptic curve. The RQ is the regulator, the elliptic regulator for the elliptic curve over Q. This omega term here is the volume of the unit ball. Okay, and so that's just pi r over 2 divided by gamma r over 2 plus 1. Okay, and so in the case you're looking at r equals 2, you get the standard pi r squared, okay, and so on. Okay. This error term, again, like I said, is completely explicit. We've got a completely explicit constant there with an error on the order of log d to the r minus 1 over 2. Okay. So in order to prove that theorem, like I say, we need to be able to show that we're mapping from points on the elliptic curve to class groups that are or to quadratic forms that belong to distinct class groups. And so what we want to look for are points with a small alpha term. And we're going to do this using the theory of heights for points on the elliptic curve. Okay? So let me briefly review those ideas here. So if I start with a point on the elliptic curve, a over c squared, b over c cubed, okay, we assume that this is completely reduced, then the naive height is the max of the absolute value of the numerator and the absolute value of the denominator. Okay? So the naive height, we're looking specifically at the x-coordinate, and we're just looking at the max here. Now, if you are used to learning about elliptic curves, reading Silverman or most other descriptions, the naive height is usually split up into local components and global components. But if you combine all of those pieces together, this is the description that you ultimately come up with for what the naive height looks like. The V, or the logarithmic height, is simply the logarithm of this naive height. And then the one that we're going to really care about is the canonical height, which is given as a limit of logarithmic heights as we take multiples of p. Okay, so as described there. So this canonical height seems a little bit weird. Okay? The question that we're interested in is most easily phrased in terms of the naive height, but the canonical height has very nice properties that we want to be able to use here. Okay? It turns out that the canonical height of a point is 0 if and only if the point is a torsion point. It satisfies a parallelogram law, which is not satisfied generally by the Weil height. It's also very close to the Weil height, though. Okay? There's a normalization issue here, the way that Silverman defines things versus some other authors, and so we need to have a half here. But essentially, the canonical height is, or the Weil height is an approximation of the canonical height that's maybe easier to calculate, but this tells us that the canonical height is if we can bound the canonical height, then we've got to bound on the Weil height up to some bound here, which is can be made completely explicit in terms of the elliptic curve. Okay, Silverman has a bound for that. There's several authors that have improved on Silverman's bounds in various cases. But we're not going to worry very much about what those bounds are. It's simply enough for us to know that there is some bound for an elliptic curve, so that this is always true for every point. Now what we want to look at is moving from our points of an elliptic curve to a lattice in r to the little r. Okay. So it turns out there is a nice linear map from the group of points EQ into r to the r, so that this lattice is full rank. We also have that the norm of the image of any point is equal to, so the norm squared is equal to the height. Okay, and the inner product of any vectors in the lattice are equal to the height pairing between those 2 points in the elliptic curve, where the height pairing is described as shown. If P is any fundamental parallelepiped of this lattice, it turns out that we know that the volume of that fundamental parallelepiped has to be the square root of the regulator of the elliptic curve. And this is a nice description here. So the canonical height allows us to basically translate our question of points on the elliptic curve to a question about points inside of the lattice. Oh, we also know that the kernel of this map is, in fact, just the torsion point. Okay? So if we want to count these points with the small alpha term, okay, we can translate that problem. Oh, there's a jump there. Okay? Basically, that small alpha term is less than or equal to this small bound times the naive height of a point. We want to make that less than square root of absolute value of our discriminant over 4. And it turns out that that's the same thing as counting points with canonical height less than this particular bound as a logarithm of d over these factors. Okay. And this is a standard lattice counting problem inside of our lattice. Okay. It turns out that these standard lattice counting arguments tell us that the number of points in of a lattice inside of a ball of a given radius is approximately equal to the volume of the unit ball in r to the r divided by the volume of the fundamental parallelepiped times 2 to the r, which we can approximate by, or which for our particular case, we're going to take the volume of the unit ball times 2 to the r over 2, and then we're replacing the volume there with the regulator. I'm sorry, up here on the top, there's supposed to be the radius of the ball that we're looking for. So again, we should have that capital T to the r halves up there. Okay. And so these lattice counting arguments tell us that this is the main term here. There is an error term here somewhere on the order of T to the r minus 1 over 2. There's some ways to improve that, but this gives us a nice description of the error. Even though I'm not going to describe that for you today, that's what we're looking at there. Okay, we get an explicit error term. So we were also able to reverse the process to using a bound on the known bound for the the known bound on the class number to tell us something about a lower bound for the height of non-torsion points on the elliptic curve. And so this was in a follow-up work with Ken and Wei Lun. We looked at this process. Okay, suppose we start with a point on an elliptic curve is a point with infinite order, and then suppose that we pick a discriminant so that the twist of the elliptic curve by that discriminant has, again, a suitable point, which I'm not going to describe what those conditions mean, but suppose it has a suitable point, then it turns out that the canonical height of that point has to be larger than some explicit bound that we can give in terms of constants of the elliptic curve. Now this is an interesting problem here. There's been several papers talking about lower bounds for these non-torsion points. The problem there is related to the question of proving that you've got a generator for the non-torsion part of the Mordell-Weil group for the elliptic curves. But there are several other authors who have given lower bounds. And our lower bound, we tried to compare it to some of the other authors, but in some cases, it's very difficult to compute some of the bounds given by some of the authors here. Okay, so Anderson and Moser back in the 80s, back in 1980, gave a particular bound here. Lambda or gamma is computable in terms of the Weierstrass P function and sigma, but it's a difficult computation. Tissery, Hendry, and Pazuki gave another description that's a little bit easier to compute. Okay, well, quite a bit easier to compute. It's still a little bit difficult to compare directly to our theorem generally. One thing that we can say is that pretty much in all cases here, the bounds are orders of is about an order of magnitude off. It's much smaller than what we actually observe, but it is a bound that we can establish there. Okay, so let's see. Yeah, so in general, these bounds are orders of magnitude smaller than the truth. Okay, so one other question that I wanted to talk about, this is going to connect to the REU project. So as I mentioned before, Buell and Soling proved their maps were linear. So they proved their maps were linear. They did this using Dirichlet composition, which is not always an easy process. Dirichlet composition is well, it's explicit, but yeah, not very straightforward. The REU used a different approach. They used Bargava cubes to prove this linearity, which so Bargava cubes are related to Dirichlet composition. It's an equivalent process, but they're much easier to work with. So Bargava described these cubes in his thesis. It gives a much more natural feeling description for Dirichlet composition, and so the REU was able to they were able to construct Bargava cubes using the map that we described, and because they're able to construct a Bargava cube, they're able to show that this map is linear. Okay, so basically. You start with an elliptic curve and a discriminant so that the twist by that discriminant has a suitable point. Then this particular map, again, we're taking little d to be 1 here. And then our Q point here is fixed. This is linear. Okay. And their particular problem that they were interested in, they were curious about when this map is not just linear, but when is it an injection into, when does it inject the torsion group into the class group? And this is an interesting question because we know something about the torsion subgroups of elliptic curves, and given infinite families of elliptic curves with given torsion subgroups, they're able to use those to find infinite families of class groups that have subgroups isomorphic to those torsion subgroups. And in particular, that tells you sometimes primes that divide the order of the class group. Okay, so assuming the hypothesis of their theorem, there are infinite families of class groups with subgroups isomorphic to these various groups that are coming from torsion subgroups of elliptic curves. Okay, so just a quick review of the results that I talked about. We have this generalized map from these two twists of the elliptic curves to the class group. We were able to use that to give explicit lower bounds on class numbers and lower bounds on the non-trivial on the heights of non-torsion points of elliptic curves, and then this nice result from the RU about these explicit subgroups of the class group. Okay, so that's what I wanted to talk about. Again, thank you so much for letting me join you today.
Okay, thank you very much.
The echo, I guess.
Hello, is there any question?
Oh, why is this? I think there is echo at your place.
No.
On my side? Okay.
Yeah, is there any question?
Okay, so I can't see any question in chat box. Yeah, at his place. I don't know if you use microphone, then there will be okay, because you are using in speaker. That's why it is coming.
Oh.
It is no. Yeah, thank you, Michael.
I think there are two devices. Upper is echo is coming. If anybody using two devices at a time, then it will be echoing.
Oh.
Now it is stopped.
All right. So start the next talk. Next talk is by Professor B. Ramakrishnan. He is currently at the university he is HOD of Department of Statistics and Applied Mathematics, Central University, Tamil Nadu, and he was working in HRI for long years, and he moved to Tamil Nadu last year. He completed his PhD from Ramakrishna Mission Vivekananda College, Chennai, under supervision of Professor T.C. Vasudevan, and he joined HRI after 2 years of postdoc at MedScience and MedScience. So his area of research are automorphic forms, theory of modular forms, integral weight, half-integral weight, higher degree modular forms, Jacobi forms, and so on. And I invite Professor Ramakrishnan to give talk on similar lifts of a second class of modular forms. Yeah, over to you, sir.
Okay. And I also thank the organizers for the kind invitation. So when I got this invitation, I was thinking that this will be the only talk on 22nd, but it has become a hectic day for me because I have to ask the excuse from the organizers that I will be leaving the meeting after my talk because I have one more talk, and I also arranging a talk from my department side in the afternoon. So those who attended the NCM workshop on which I gave a set of lectures last week, I lectured on this one also in one session, and then most of the content will be of the same, but only of the new information I added. So for you who attended it, you can see some new information at the end. Okay, so I have to
Present now.
Yeah, I'm doing it. So many things are there. Is it visible now? Is it okay? Is it with?
Yes.
Are you able
Yes.
to see that? Okay.
Yes. Yes. Fine.
So this is about some property of Shimura mapping on certain class of modular forms. The whole thing started with some observation of the Selberg. It seems to be that this observation made by Selberg before the Shimura correspondence came was generalized after the Shimura work by some authors, and this is a report of that particular piece of work and my recent research result in this direction. Okay. So before I go to the problem, so I have to give us introduction to theory of modular forms for those who are not familiar with modular forms. A brief introduction to the theory of modular forms of half-integral weight. It was systematically developed by Shimura in the year 1973. That is famous paper. So the theory was developed mainly by using the transformation formula of the classical theta function, which is given by this. Theta z is summation q power n square, where q is the variable e power 2 pi I z. So Hecke proved that this theta function satisfies the transformation, this one, for any matrix gamma in gamma 0 4. Theta of gamma z is j gamma z into theta z, where this automorphic factor replaces the usual automorphic factor of Cz plus d in the case of half-integral weight. So this consists of a quadratic residue symbol c by d, and then this is the fourth root of unity minus 4 by d power minus half, and then the square. One has to fix a square root having the argument between minus pi by 2 to plus pi by 2. So with that square root fixing, one can work with the case of modular forms of half-integral weight. So this transformation was derived by Hecke. So what Shimura did is that replacing this usual automorphic factor by this extra fourth root of unity, together with that he considered the group, a bigger group, and then define what could be the generalization of modular forms of half-integral weight. So we'll just give a formal definition. A holomorphic function defined on the upper half plane is called a modular form of weight k plus half on gamma 0 4n with character if this f satisfies the transformation. F of gamma z is j, the character chi of d, j of gamma z, the same j gamma z I take it, power 2k plus 1, where the matrix gamma is written as ABCD. That right lower entry is the d. So chi of d, j gamma z for 2k plus 1 f of z. So this can be written in terms of these factors, but I'm simplicity I'm writing this. So together with this transformation, if f is also holomorphic at the cusp of gamma 0 4n, then f is called a modular form of weight k plus half with respect to the group character. So note that chi is an even Dirichlet character modulo 4n. Unlike in the case of integral weight, one can have odd character also, which has equal to the parity of the weight k. So chi of minus 1 equal to minus 1 power k in the case of integral weight, but here for the weight k plus half integral, the chi should be an even character. So after this modular form definition, if the function f vanishes at all the cusp, there is a concept called vanishing at the cusp. Then basically it is the expansion at the cusp, including infinity. It should not have any negative term in the Laurent expansion. So then it is called including the 0, then it is a cusp form. The notation is m k plus half 4n chi is the space of modular forms of weight k plus half of gamma 0 4n with character, and similarly S denotes the space of cusp forms. And there are usual Hecke theory developed in the case of half-integral weight. The Hecke operators are pp square for p not dividing level 4n, and this u operator for the primes dividing level. These are the basic things in the case of. So Shimura introduces the theory as well as the Hecke theory in that paper. Okay. So in order to get a correspondence in that paper, I think one of the main thing is that is by considering a Dirichlet series, special Dirichlet series, is constructing a correspondence with the space of modular forms of weight 2k. So for that, he took the Dirichlet series, given a modular form, and the AF is a Fourier coefficient of a modular form. You take the Dirichlet series of this type, AF of Tn square n power minus s, and assume that f is an eigenfunction with respect to Tp square as well as up square, that means with eigenvalue lambda p. So there is a relation among the Fourier coefficients because of the eigenfunction relation. Use that relation, and then we could prove that this Dirichlet series is written in terms of this quotient of the two L functions. One is the numerator is the usual Dirichlet L function with respect to this character, minus 1 over kt by dot into chi. The denominator is another Euler product of formed out of eigenvalues lambda p, and then there is a chi p square character appearing in it. So this is the Shimura correspondence. So what you do that you take the L factor to the left hand side, and then that becomes a Dirichlet series. You take the product of the two Dirichlet series, and this what he proved is that this also Dirichlet series of a modular form. That is the major part of his work. So therefore, the Shimura correspondence is represented by this particular Dirichlet series expression for this AF of Tn square and power minus s. So after that, you do the manipulation of this Dirichlet series, and then I can write this L factor come to the left, and then you write it. The inside coefficient is nothing but the product of the two Dirichlet series coefficients, summation n, d dividing n, d relative prime to 2n. So that condition is automatically coming because of the character appearance there. Minus 1 4 k d by d, chi of d, d 4 k minus 1, af of Tn square by d square q1. This is exactly the Dirichlet multiplication on the left hand side. The right hand side, this Euler product is given by a Dirichlet series of this type. That was the major proof of that major part of the paper of Shimura, which he says that given f, one can find a capital F, which is a modular form of weight 2k, and some level. This level was fixed by the work of Niwa next year. So Shimura conjectured that level is exactly the half of the level, and with the character chi square. That's what it is appearing here. This eigenvalues of capital F is exactly the eigenvalues of the F under the Tp square. So the one AF of T factor comes out when you do the n equal to 1. This is the factor comes out, and capital F is a normalized form. So the if I do this one, therefore the association, the small f going to the capital F by this is called the T Shimura correspondence. So for every square free T, so one obtains this one provided this Tth coefficient of F is non-zero. Otherwise, it becomes maps to 0. So you have to take this Tth coefficient to be non-zero. Then I consider the Shimura map, and then it takes the form F to capital. So this is the correspondence which we will be using in our today's lecture. So in this talk, we shall discuss about certain property of this Shimura map, but not on all modular forms, for a class of modular forms of half-integral weight. So it started with an unpublished work of Selberg. As I mentioned, that this was observed before the Shimura's correspondence. So what he observed is, take F to be a normalized Hecke eigenform of weight k with respect to the group SL2Z, and then consider this function. If I multiply F into theta, it is a half-integral weight form, because F is a weight k form, and then theta is a weight half form. If I multiply, I can get a modular form of weight k plus half. So yes, little bit modification it does. So the F of 4 is a times theta is a, so it is a weight k plus half modular form of level 4, and then weight is k plus half. So then consider this particular product, we call it as capital F. So what Selberg showed that the previous slide, I think I mentioned this this ST map. You put t equal to 1 in this. When I put t equal to 1, this will be only minus 1 4 k by d will be there, character chi of d. When you take the level to be 1, this character also vanishes. So since you are talking about the SL2Z map, so this factor will not be there. So without that AF of n square by d square. So that's what you have to see. So what he showed is that if I apply this t equal to 1 map for this particular function, the image is exactly given by the square of this function we started with and its duplication difference. In other words, in terms of the operators, it is S1 of the Shimura first image of capital F is F square minus 2 power k minus S square of 2. So this is the observation made by Selberg. So it gives the mapping without going to the bigger theory. So one can do without going much about that. With simple calculation, one can show this. Okay. So to prove this observation, so Selberg uses the multiplicative relation by the Fourier coefficient of F. That is the main thing in this whole talk. Okay. And also one uses the inversion formula. So extension of Selberg method, I will come to this work of Selberg, that's what I will describe in detail, but all other extensions are exactly similar, so I will not go into the computational details of the extension. So I'll just give the history of what is the known results in this one. So expression of Selberg's method, it was done by, started with the Cipra's work, appeared in JNT in 1989. So what he does is considers the generalized theta series function, h psi z, if 1 by 2 factor is extra, so psi of n power nu e power 2 pi I n square is z, where for each psi primitive, this was considered by Shimura in his paper. So these theta series were considered in his work. So psi is a primitive Dirichlet character modulo any conductor R, and psi of -1 is -1 power nu. So if it is an even character, this n power will not be there. If it is an odd character, n will be there. That is the only difference. And instead of the Hecke form of level 1 in Selberg's one, Cipra used, I should not have written new form here. One can take any Hecke form of weight k and level n with character. What we need is only the Hecke relation. So it is an Hecke form. That is the only relation we will need use in this problem. Okay, so F is a Hecke form. And then the capital F is, the previous case was f of 4z times theta. Here he is multiplying by p power mu, where this conductor R is a, I think I should have written something, okay, then I can take the same mu. So R is a power of p, so I just put the f of Rz into this generalized theta function. So we consider the capital F, and then instead of g is the square of f, instead of that, because it is a level is involved, so f g is f z into f of p power mu z when psi is an even character, otherwise some derivative of f involved. The derivative combination also is a modular form. So this is a modular form of weight 2k, this is a modular form of weight 2k plus 2 because of the derivative involved. So that is the only difference. When psi is odd, there will be weight 1 added there also, and there will be weight 2 added here. So therefore, this is the starting this one, and then the final function, the mapping function, capital G is nothing but, I take the psi twist of G. So psi is a Cn e power 2 pi n, where Cn is the nth Fourier coefficient of G. So given any modular form, I can twist this modular form by a character. That means I consider the Fourier coefficients multiplied by the character value. So this is again a modular form, but level will be increased. The weight remains the same. So the capital G is also weight 2k form, or 2k plus 2 form, weight form, with level multiplied by the conductor square. So R square or p power 2 mu will be there. So this is the setup in the case of Cipra's work. Generalizes the level 1 form by a level n form, and then this capital F is little bit changes he has made, because in previous case the no character, because of the character involved, he has to put the conductor of character in this one, and then theta is also generalized. So with the above setup, Cipra, what he showed, that if I take the same S1 map on F, the function F defined above, it gives Gz up to some constant G of 2z. So if you look at the Selberg's one, S1 of F is F square minus some 2 power k minus n F square of 2z. And then when I replace this by the, the generalized theta series, the result is exactly same. I have a function G, which is again which is the square of this G with some kind of modifications, and then its duplication G of 2z. Okay, so this is again constant coming because of the extra assumptions. So capital F is a form in Sk plus nu plus r, that nu will be 0 or 1 according to psi is an even character or odd character. Okay, so therefore this is the, also one can do that simple calculation that what will be the level and then weight, etc. From there, a capital F is a form of this half weight form, and Gz is a form of level n1 chi square psi square, where n1 is nothing but LCM of n times p power mu and p power 2 mu. So, and chi minus 4 is the odd character modulo 4. So this I have to compensate because I need a character, even character in this case. So this is the setup obtained in the work of Cipra. After that, 2008, there are two authors, Hansen and Nakwi. They further generalized this particular construction, but in removing the restriction that psi is a character modulo p power mu. So take any integer r, psi is now is any integer r, any character primitive Dirichlet character modulo any integer. So that was the main thing. So the extension work. Psi is a primitive Dirichlet character of modulo any positive integer. Now I'll just mention this result of Hansen and Nakwi. So take psi to be a Dirichlet character modulo r is a product of prime powers you write. You split the psi also in terms of the psi I, where psi I is a Dirichlet character modulo of pi power alpha I. Also let psi of -1 is -1 for nu. So either even or odd character according to nu is 0 or 1. So now take a Hecke eigenform of level n character chi and then define capital F to be again same thing like Cipra 4 times R is Z, there is P power mu. Now the conductor is R, 4R is Z, his size. So that is same function you consider. They belong to Sk plus mu plus R, 4 dash n dash square R square. Now the n dash definition is exactly n by the GCD of n comma R. That's easy bit. Modification is there. And chi minus 4 is the odd character because I need a character even here. Therefore, this adjustment has to be done to the spaces. Now define small g. In the previous case, the first one was a square. In the Cipra's case, it was product with some duplication, and second one is involved in derivative. In this case, since R is any integer, the generalization is like this. One has to take g to be this particular combination where d divides R and d comma R by d equal to 1. So I have to put this ID of -1 to make it automorphic. So this is a modular form of weight 2k of level, particular level one has to find out. And this one, when I take the derivative, I have to take the linear combination. It is weight 2k plus 2. Okay, so then once it's g is there, g psi is there, that capital G is exactly the g psi which I mentioned earlier, that summation psi of n, c of n, e power 2 pi I and z. So that take the psi twist of small g, that is g psi. Now with this same setup, take the Shimura 1 map on capital F, and is exactly the psi twist of this function and this particular constant time the duplication. That's what they prove. So this is a more general result. Whatever Selberg's observation is done extension to the maximum level. So nothing more, no more generalization is needed now. So this is what the whole setup is mainly for proving a special property of the Shimura 1 map t equal to 1 map on certain class of functions. So now at some point I think one should notice that if since h psi is a theta series, f is a modular form, I am taking this f 4R is that this particular combination is always belonging to a subspace of modular forms, which is defined by Conan. So they belong to the Conan's plus space. That at some point I think we will make that observation. But right now this, so therefore in some sense this whole results are, even start with this function. This function is in the Conan's plus space. It was the work of Conan in 1980. He introduced a subspace of the full space of modular forms with some Fourier coefficient conditions. So this function satisfies this condition. Therefore, this lies in the Conan's plus space. So the Selberg's one is giving the image of the Shimura map on this function which belongs to the plus space, which is taking this particular stop. Okay. So there is also a Shimura's map defined by Conan on this restricted to subspace that we denote by S1 plus or something because of the plus space. Later on, I will say that. So rather than considering the Shimura Conan map on this, they consider the Shimura map. What will be the image? The image is exactly this gold class. So these things we will come to that earlier. So this is one by Cipra. The second result is by Hansen Nakvi, more general things. Now in my work, what I did with my former student Manish Kumar Pandey, this appears to appear in the IGNT. We generalize this. What we saw is that y to only take t equal to 1. So this construction, everything is set up, everything is there. You do minor adjustment here and there. I can imitate the same kind of methods and still get the similar property for any t to Shimura map. So that is our observation. So that's what we did. So joint work with that is, our observation is that the same type of arguments can be applied to get corresponding results for the Shimura ellipse indexed by square free integer. So arguments, not only arguments, so the function construction, everything is exactly the same, but you have to do a little bit modification in the definition of the original function for which we need the map. Okay, since the method is similar, we get a relation between the image of, so there is also a image of S1 is there and there is also a ST map involved. We get a relation between these two on some functions. At the end, we will mention what it is. So as in, this is why I am describing that instead of putting it a theorem. Did I mention as a theorem? Yes, before that I just. So as in Hansen Nakvi's theorem, psi primitive Dirichlet character modulo R, the same assumption. Hecke eigenform is level n with the character. G is exactly the same function as in Hansen Nakvi's result. Again, write R as the product of prime powers. split the psi as a primitive character modulo psi p power I, pi power alpha I, and then for each d divisor d or dividing r with d comma r by d equal to 1, psi of d is given by product of psi j where pi power alpha j divides d. So that also I take. So for a modular form f with Fourier expansion f of z equal to a n of e n of z, define the function gt z by, I think I did a mistake. Yeah, for this one gt, g is there, f is given, a coefficient is a of n, g is the function of any function Hecke eigenform. Gt of z is, I multiply the at coefficient times g of z. So I just defined gt of z as g times the a of t. Assume that a of t is non-zero. So I have to find a non-zero Fourier coefficient at for which it is non-zero. So g is exactly the function as in Hansen-Naquin's result. So corresponding to the character psi modulo r, you take the theta function h psi z as a generalized theta function as defined earlier. So this is the setup in our paper. So theorem. So take f to be a normalized Hecke eigenform, sk n chi, t square free positive integer such that t divides n. There are two results we have. One, where the square free t divides the level n, and one without the condition. The first one will define what is the image when t divides n, and assume that t comma 2n by t equal to 1. Okay, so therefore, there is a square free condition on n also, because t should be a square free. So psi be a primitive Dirichlet character modulo r with r comma t1. So r also should be relatively prime to the given map t. So set ft of z, f of 4r is z, h psi of t z. The difference here is that we take the same function f of 4r z into h psi, but only I am duplicating this h psi with this t. So when t equal to 1, f1 of z in Hansen-Naquin and f1 of z in our definition the f set. So t equal to 1 means it coincides with Hansen-Naquin's result. Then ft of z belongs to sk plus mu plus half 4 times n dash r square. N dash is exactly the same, n by gcd of r, and n chi psi. There is, because of the duplication in half integral weight, one character, quadratic character will come, chi t will come. These characters are defined by chi m is nothing but n by dot character. So it is a character modulo n or 4n. So chi t, and there is a chi minus 4k plus k. This is the only difference here. So then f, given Hecke eigenform, I define gt as above. So that means I take gz by Hansen-Naquin multiply by a of t, then that is my gt. So given f, we define gt as above, and capital GT is nothing but the psi twist of gt. Twist the character psi of n, c of n, where cn is the nth Fourier exponent of gt. So with these settings, what we show is that if I take the Shimura map, apply that on ft, that is exactly giving in terms of the gt function and its duplication. So the result is exactly the same, and it belongs to s2 into k plus mu 2 n dash r square chi square. So this is our result. Again, the method is exactly the same. Therefore, I will not give the proof of this one, but you will see the proof of the method of Selberg. So that will show you that how the thing is proved. So due to the assumption that t comma n by t1, the tth Fourier coefficient at is non-zero. Note that f is a new form. Whenever square divides that one, p square divides n, the tth coefficient is 0. That's what we have to put this condition such that a of t is non-zero. Otherwise, there is no point in considering this map. So the function gtz is non-zero. We also remark that by our construction, gt is nothing but at times g1 of z. The g1 is the g function defined in Hansen-Naquin's result. Therefore, the gt is nothing but at into g of z. So that is the one. And also that f1 of z is f of z. So in our case t equal to 1 means Hansen-Naquin's capital F. Therefore, if I use theorem 1, st of z is nothing but gt of z. I have gt of 2 z. Then you replace gtz by at into g1 of z. Then I have at into g of z here, g of 2 z. So the inside quantity is nothing but the first Shimura image of the function f defined in Hansen-Naquin. Therefore, by our construction, we have a function capital Ft. Okay. If I apply the Shimura map on that, and there is a f1 map constructed by Hansen-Naquin, and there is a first Shimura image of capital F. Therefore, these two they are related like this. Just I am multiplying by at, that is the only thing. So the only difference is that the image is exactly the constant time a of t times the image of Hansen-Naquin. So this is one observation we made. Now our second theorem is without any condition on t, no condition on the square free. So f be a normalized Hegelian form, same condition, psi primitive derivative character, t square free integer without any condition. Now what I do, in the earlier work there was only the t duplication on the theta series, but here I put the t so that the t cancels out, so that you multiply by t z here in f also. That is the only difference. That is my capital HT. And then one can show that the escape HT belongs to k plus mu plus half, and there is a t appearing here also. Chi f, chi psi, chi t, chi minus 4, where n dash is as above. So corresponding to f, g be the function defined by 1. 1 means, I think Hansen-Naquin, if I'm right. Yes, g is the function defined as in Hansen-Naquin's result. I'll come back to this. Yeah. Defined by 1, and capital G is the psi twist of G. Okay. Then G is in the space f s of 2 k plus nu n dash r square chi square I square, and I can consider the t Shimura lifting of this capital HT. Now this G is the image that construction in Hansen-Naquin. Then I have to apply all the duplicating operator for primes dividing the number 2t. Earlier only the duplication with respect to p equal to 2 was there. Right now, because of the teeth map coming, all primes dividing t also coming into this place here. So this belongs to s 2k plus nu 2 the n dash r square t chi square s. So where b of d is the operator, where f bar bd is f of d. So this is the result more in general without any condition. Now we make so we will now demonstrate. I will come to the remark a little later. So I will just demonstrate. These are all the results which I stated. One is the Selberg's observation, the Tsipra's result, Hansen-Naquin's generalization, and then our result. So we will just see how this is proved. Okay. So for simplicity, we demonstrate the method of Selberg. The main ingredients in all other works are the same. Therefore, no need to bother. So an is the multiplicative function satisfying the relation. An is the Fourier coefficient of the given K eigenform. It satisfies this particular relation. Okay. Am into an is summation amn by d square d dividing m. Actually, d dividing m comma n I have to write. That is the wrong thing I do. So this condition should be there. That is the mistake. D dividing the GCD of m comma n d power k minus 1 amn by d square. Therefore, if I take the inversion of this, they are referred to as the Selberg inversion formula. I can find mn in terms of m by d, n by d, just Mobius inversion you take it. So this is the main inversion formula which we use in that, apart from the Dirichlet series manipulation. So if small f is a Hecke eigenform with coefficient an, I consider the f of 4 result into theta z. I write it as the nth coefficient is b of n, then b of n is nothing but a of n minus m square by 4. Where m square is strictly less than n. So therefore, this is a finite sum. But in future, I will write only m integers, but it's not an infinite sum, but it will be a finite sum only. So for this relation gives you that the bn coefficients survive only when the coefficients are n is a square modulo 4. Only it survives. Okay. Therefore, whenever n is a square modulo 4, only this survives. Therefore, it belongs to the plus space. This is the proof of that. The particular function belongs to the Conan plus space. So therefore, b of n is there. In the Shimura map, this b of n square I need it because a of t n square by d square, therefore n square coefficient I compute. B of n square is replacing n by n square, I get it. So I can factorize this n square minus n square by 4 into n plus n by 2 n by n by 2. And then after change of variable, this is changed to a of m into n minus m with m again deranging from 1 to n minus m, n minus 1. Therefore, I have a of the product of m into two integers. Therefore, I can use the inversion formula here. I apply this inversion formula in this particular place and keep the sum over m as it is. So this is using inversion formula d divides m comma n minus m mu of d d power k minus 1 a of m by d a of n minus m by d. Okay. So then do simplification, it turns out to be that only d dividing n will be there. I can replace m by md, therefore the condition will go away because this implies d dividing n and d dividing m. I can replace m a multiple of d and get rid of the condition. So after that it becomes d dividing n mu of d d power k minus 1 a of m by d minus m. So therefore, I can just take this d dividing n outside, sum over m. Now look at this particular sum over m, a of m, a of n by dm. This is exactly the c n by d coefficient. So if you look at the definition of small g in this one, if I consider this f square in this, what did I write? After Shimura correspondence, this will come. Yeah, f square. When you do the f square, f is coefficient is an. This coefficient square of the f square coefficient is given in terms of summation over m, a of m into a of n minus m. That is the coefficient of g. Where did I write? And here, yeah. So this is exactly the coefficient of f square with n replaced by n by d. Therefore, this is c of n by d. So that is one observation we make. Therefore, b of n square is given in terms of summation d dividing n, b of d power k minus 1 c of n by d. This again looks like some Dirichlet series product. So, okay. Therefore, when I take b of n square, this is I sum overall. I consider b n square. Therefore, I take the Dirichlet series with left hand side multiplied by n power n minus s and sum over n to 1 to infinity. Right hand side also I sum over n equal to 1 to infinity. So I have left hand side Dirichlet series. Right hand side also Dirichlet series. So this is inside one, the product of Dirichlet series. One is the Riemann zeta function at s minus k plus 1 inverse, and the second one is the Dirichlet series corresponding to f square. So this splits into these two things. Now, as I mentioned in the beginning, the first slide tells you that to get the Shimura map, I have to multiply by some L function on the left hand side. That is exactly the L function for t equal to 1. So for t equal to 1, I have to multiply by L s minus k plus 1 chi minus chi for trivial character modulo 4 on left hand side. You do the multiplication on both the sides. Left hand side is nothing but the Dirichlet series corresponding to the t equal to 1 map. Okay, that is the left hand side. The right hand side, if I do simplification, so left hand side is exactly the a1n. This is nothing but the nth Fourier coefficient of s1 of capital F. Okay, so this is 1, and Dirichlet series is nothing but this cancellation. Numerator has Euler factor p not equal to 2. Denominator has all primes, therefore only p equal to 2 will remain with this Euler factor. That is exactly 1 minus 2 power my k minus 1 minus f. This Dirichlet series as it is. So you multiplying these two and changing this Dirichlet series into modular form, what we get left hand side is nothing but the first Shimura image of capital F Dirichlet series is exactly the first one is f square Dirichlet series, second one is f square of 2 is the Dirichlet series. So by this identity, what we get is exactly the Shimura image of capital F is given by f square minus 2 power k minus 1 f square of 2 is there. Exactly the Hilbert result. So the method is completely simple and then uses only the multiplicative relation of the Fourier coefficient of the given Hickey eigenform and this particular inversion formula, which is one can use. Now, and then observing that this Shimura map is given by this particular product. The whole technique is exactly same. When you introduce the more general variables, level, character, everything, the more complications will come. So, but the result is exactly the same. We shall now present some examples to demonstrate our results. Okay. Before I go to that, there is a remark. One remark is that so we did not have any condition on t in the second result, but if you look at both the results, the level of the half entanglement form is always divisible by t. So that means effectively both the theorems, both generalized theorems, they are concerning the deep Shimura image of certain modular forms whose level is divisible by t. Therefore, when I talk about the Shimura, this kind of property for Shimura map other than t equal to 1, I need to consider functions whose level is divisible by t. So the method of proving these results suggests that this type of construction, I should not say may not give information for the t Shimura map on forms of integral weight whose level is relatively prime to t. So that will be an interesting thing. Whether one can construct forms whose level is not necessarily a divisor of t, can one do this kind of calculation? So that we have not, looks like this construction involves with this property only. The second property is that in theorem 2, if you take t such that GCD of n comma t greater than 1, so there is no condition on t. Suppose if I assume in the theorem with the same construction, if I take the GCD of n comma t greater than 1, then the level of image goes down by a factor of GCD and comma T. So therefore, the integral image again level is reduced in this particular case. For example, if you take T dividing n, then STHT belongs to the space S2 k plus u 2 n dash r square psi square, which is a proper subspace of 2 n dash r square T. The same is true if T has a factor with the conductor R also. So there is another one can do that. More precisely, the level of the image of the Shimura lift in theorem 2 is given by 2 times r n dash r square T divided by the GCD. So I have to remove the GCD of nr with T with T. Okay, so whatever it is there, I just remove it, then the image will be reduced by this particular number. So this is the second observation. Now we go to the examples. So example 1 is again take the trivial character usual theta function. I take a new form of level 12, weight 3, therefore the odd character will be there, and consider the same theta as the usual classical theta series. This small f is a new form now, given by the product of the eta function, eta cube 2 is there, eta cube 6 is there, and then f3 is there because I am taking t equal to 3 in this case, and f of 4 is there, theta of 3 is there, that t I have to put in theta. So this belongs to S3 by 3 plus half or level 48. So now capital N is 12, T is 3, so therefore take GT of Z is, I have to multiply by S square by AT, which is AT into F square, which is equal to minus 3 times F square is there, which is the weight 6 and level 12 form. Now R equal to 1, we have G3 of Z is small g3 of Z, and which is minus 3 times F square is there. And as n equal to 12, the character is the character modulo 12, therefore chi of 2 is 0. Therefore, in the image there is no chi2 term, this term will be vanishing. Therefore, the image of F3 under S3 is exactly minus 3 times F square. So level 12, weight 6 form. This is one example using our results when the case the T dividing n. Example 2, we take psi to be the Legendre symbol because earlier the psi was trivial, that T r equal to 1, in this case now r equal to 5. So Legendre symbol dot by 5, so r equal to 5. Take a new form of level 6, weight 4. Then n equal to 6, t equal to 3. So the t does not divide. The 3 divides 6. Again, t dividing and second theorem. So n dash is n equal to 6. One can compute. A of 3 is minus 3. The capital F3 is this one, which is level 600. Character is 15 by dot. And G3 is this combination. Therefore, this is a level 30. H psi is, this is a theta function, n by 5 e of n square is well. So the G3 is in level 8, weight 8, level 150. The side twist is G3. And then we have the image of F3 under S3 is 150. So chi of 2 is 0, therefore again the second duplication will not be there. So another example. Third one, we shall take psi to be odd Dirichlet character. Earlier it was even character, so now I take the odd character dot by 3. Then take F to be a level 7, weight 3, again odd character. So n equal to 7, I can take t equal to 7, r equal to 3, and F7 is this. And then one can do this computation because in this case of odd, and then I have to take the g to be the derivative combination. It will be weight 8 and level 21. And G7 is the twist I have to take. By theorem, we have S7 of F7 is G7 plus 8 times F. This is level 126. And again, I take the illustration remark made at the end of theorem. We consider the new form. So level 12, weight 3. As an example, take r equal to 1, therefore classical theta series. Chi is a character modulo 12. So by chi 4 into dot by 3. Then example 1, we have S3 of F3 is A of 3 F square. That is in the example 1. And then this theorem C, in fact, theorem B I wrote. This is, I think, Hansen's theorem. Modular form of or Sipra's theorem I have to do. The modular form 3 is in this case. F of Z is F of 4 is Z, theta is Z. I2 is 0. The image of F under S1 map is F square. Therefore, S3 of F3 is nothing but A of 3 into F square, which is the first image of this capital F in Sipra's paper. So this is the one which I mentioned, that I consider the F3 of Z, and then I take the Shimura image of F3, which is exactly the F map, F function under Shimura 1. These two are related like this. Just multiply by the A3 coefficient of small f. Now some example 5. In example 2, psi was dot by 5 modulo r, and then I take here t equal to 7, n dash is n, and in this case we have this. One can work out of this all the for this function. I can just write down all everything. The image is exactly same. G is plus 343, g of 7 is there. And example 6, we take in the previous example take t equal to 5. So there is a character modulo 5. I can also take t equal to 5 in this. And f and g are the same in example 5. So h5 is a level 3000, weight 4 plus half. And then since chi n is even, chi is 0, chi of 2, and t equal to r equal to 5 implies chi of 5 and psi of 5 are also 0. Therefore, if I take the t equal to 5 map on h5 is exactly gz. So therefore, the level is even further reduced by 2 into 5. So, okay. So originally it should have been 1500, but the original final level will be again divided by 10. So because this factor is reduced, that is what which I mentioned in the remark at the end of theorem 2. Okay. So now come to some remarks. Okay. These are the remarks I think we should related to this work. In his first work on the plus space, Conan makes the following observation. You take the normalized license series with the Q coefficient 1, not the EK but GK. So K positive integer for the full modular group, and consider this particular same thing Heke eigenform you take, multiply by 4z and theta product, it is in the plus space. Okay, he applies the first Shimura Conan place, Conan map, that is plus, then he says that is exactly GK square. So if you look at the Selberg's result, if you apply this function on S1, you get GK square minus 2 power k minus 1 GK of 2z, GK square of 2z. But on the other hand, if you do since it is a plus space, I can apply the Conan map also, that I get a simple expression on the right, which is GK square. For this computation, Conan refers to Cohen's thesis in 1976. So S1 plus is the first Shimura Conan map on the plus space, is MK plus or plus 4. That was the subject of study in his paper 1980. Therefore, it is likely that the above property is true for any Heke eigenform of weight k and in the plus space. Therefore, and I have done this calculation, I think I have to rigorously do that. It is in fact true. Therefore, the Selberg's computation one can view as follows. To take f to be Heke eigenform of weight k, I apply the f function, f of 4z theta z is my capital F, apply the Shimura 1 map, and it is exactly the capital F applied to S1 plus, that is exactly f square. Okay, that's what this is small f square comes in Selberg's method, minus 2 power k minus 1 f square of 2z. Therefore, the Selberg's one is given in terms of the image of function under S1 plus. Okay, that's f bar S1 plus is exactly f square. This is what one can see. So provided if you give this kind of result for general, so this Selberg's observation will follow from this. That's what I say. So why it is true? That's what I am telling in this slide. I think our last slide. So in our work, my work with Savalikun and Manikam appeared in 2010. So we made this following observation about Shimura map and Shimura Conan map. So take T to be 1 modulo 4 square free integer, and then take the Tth Shimura map. It is exactly given by the Shimura Conan Tth map minus this particular plus minus 1 t by 2 times 2 power k minus 1 St plus bar b2. Okay, when t equal to 1, it is exactly the previous relation. When I put t equal to 1, it is exactly this. If I look compare this one, St plus minus 2 power k minus 1 St plus bar b2. So, therefore, more generally it is true. Okay, so this is exactly the relation mentioned in the earlier slide when t equal to 1. From this observation, it follows that it is enough to prove the mapping property for the class of functions which belong to the plus space whenever the level is. So wherever this plus space is defined, I can do that. So under the Shimura Conan map. Therefore, if I prove the property for St plus, the property for the Shimura map follows. Okay, I think with that I will stop. If you have any questions, I'm happy to answer.
Okay, thank you very much for the interesting talk. Is there any questions from the audience?
So can I ask?
Yes.
Go ahead.
So the first question is at the beginning of your slide, slide you defined the Shimura map.
Yes.
So, so the image of the, so is it true that the image of the Shimura map is inside the space of cusp form for k bigger than or equals to 2?
Yeah, that is true. Yeah. When k greater than or equal to 2, they are the finer things one has to do. Yeah.
Yeah. And then the second question is, in one of your slides, you also define this this theta series.
Yes.
So my question is, when psi is a non-primitive odd character,
okay,
any results about cuspidity of the theta series?
See, the non-primitive I have not considered. Everything should be primitive in this case.
Okay. Okay.
I have not considered non-primitive one. So all these works involve the primitive character, then consider the corresponding theta series.
Okay. Thank you. Yeah.
I have one question.
Yes.
One of the example you give two different Shimura maps at the same image, yes? S3 and S1.
Repeat again.
In one of the example you mentioned at the end, two
Okay.
different Shimura maps have the same images, yes?
This is the one you are talking about?
Yeah, S3.
S3, F3 is minus 3 F square, is that? Let me see. Not here. Not here. It's before that, I think.
Before that.
The example one is this one. Probably example 4 or 5.
Shimura. I think this one.
Yeah, this is the one. Yeah.
Yeah. So is there any general region like this, or this is something very special?
No. See, when t divided in n, I told you no that at will come. So depending on your, this is the condition, no. Where did I write t to this theorem? If you look at, yeah, this is the condition, right? This gt is defined as a of t times, right?
Yeah.
Therefore, this this a of t comes in both the things. That's what I observed this one. Here, STFT is nothing but AT S1 of f.
Okay.
So in some cases, it has only one component. There is no duplication because of the character vanishing in that case. So this is exactly the relation we are asking about.
Yeah. Is there any further question?
No, sir, I don't think there is any more question in chat. So,
okay.
Okay. So let's thank the speaker.
Thank you. Okay, I will see one more and then I. Sorry for that. Huh?
Yeah. Okay. Over. Yes.
Okay.
okay. Okay. So thank you, sir. So our next session will start in 2 minutes.
Varanasi.